Yes, we are now recording. So let's get the slideshow from current slide. Okay. Before we launch into today's, let me just go over a couple of things. Number one, I can't remember if last Thursday I had all this done or not, but everything's on Blackboard now. Okay, your syllabus is there. Research paper instructions there. My locator card is there. Pictures from Hubble telescope are there. Space objects in perspective is there. A nice slideshow, well worth a look. Just interesting. Okay. All the PowerPoints are there, and I have the link from Screencast-O-Matic. And it's PHS111 YouTube videos. That's the other classes that we've had. And everything's there, of course, except today's. All right, number two. Of course, I missed all my office hours today because I was at the doctor's. In fact, I missed some of this class. In fact, are y'all wanting me to somehow find a way to make up the 45 minutes I missed? Or do you think, say again? Boy, y'all are so kind. Y'all are just incredibly kind. Okay. Saving me that extra work. Wow. My hat's off. Oh, I'm not wearing a hat. Okay. Now, but because I missed all of my trig class today, that class will be made up Thursday. And this is what I was telling, boy, I'm going blank on names. Say again? Yeah, I know. What is it? Brianna. Yeah, I just saw it. Brianna. On Thursday, normally my trig class is 9:30 to 10:45. We'll just do a second class right after that, 10:45 till 12. So I'll be in trig class from 9:30 until 12, and my office hours shrink to 12 to 12:30. Okay, so if you do need to see me after 12, I'll be coming back toward the office here, so you'll be able to catch me there. And then we'll be back to normal, whatever that, well, okay. I had hoped today to have a little time, which I didn't, to try to call Mr. Weigel at Sanford's Planetarium. The first possible day we would have for that visit would be this coming Thursday, like day after tomorrow, or next Tuesday, but I don't know if either one of those days works for him. If you had a choice, which would you rather have, this Thursday or Tuesday to go to Sanford for the planetarium? Tuesday? Okay. Well, so few people are here today to give me feedback, I think that's probably the safest thing, is to go for Tuesday. But I don't know if he can do it. So I will know on Thursday whether we can go on Tuesday or not. What's that?
Make your work study call.
He just fled the coop.
He's in space lab.
He is? Well, he's tutoring, isn't he?
That's about so we're going this next Tuesday?
Well, we may be. Is that a bad day for you?
To a museum?
No, to the planetarium at Sanford University. Yeah. They have a really good show.
Do we drive ourselves?
I can arrange to have a van, but I think the van is limited in how many can be in it. I can't remember what it, anyone remembers it. It's a 9-passenger van, but it's only allowed to have 7 in it because of insurance, or it's a 15-passenger van, only allowed to have 9. I don't know. They have some weird rules on it. So I'll try to find that out by Thursday, so I'll know. Yeah, that actually works nicely to do that, but I don't want to force y'all to. If you need to have transportation, I'll provide it.
I need to know so I can let the person, so I can have my van.
Yeah, well, I'll let you know on Thursday. Hopefully I can get in touch with him tomorrow and find out, and then we'll talk about it on Thursday and plan for next Tuesday. Or later, yeah, well, but you'll know Thursday, hopefully. Okay. Okay. All right, so there aren't any normal weeks here. Okay. We'll be sort of back to normal, whatever that is. Okay, I'm pretty sure we did this slide already. I remember going through that, and let me turn off this front light up here. Can y'all see the right? Okay, identifying place. We already said if we lived on a flat earth, I remember going through that, we would know how to do this, and you have x, y coordinates. Okay? And then I think we did this slide as well. I'm pretty sure we did. We talked about latitude. I remember that. And this is another one showing latitude. So I remember that one as well. I think we had just finished that one when we were about to start on longitude. Okay? And I think there is another, in my text, these next two slides are out of order, or they don't have the second slide. But this is how we measure longitude. Latitude starts from where? Where is 0 latitude? Say again? No? Okay, you're thinking longitude. The latitude starts at the equator. Goes 90 degrees north, 90 degrees south. Okay? Longitude, however, we don't have poles. I mean, we have poles, but you see the poles provide us a place to start latitude. Equidistance from the two poles is the equator. And that's where we start our latitude from. But longitude, all these lines are just like each other that go around the globe this way, the meridian. So we need to have a starting point. And you just said what it was. Didn't you?
I said a lot of things.
Huh?
I said a lot of things.
Yeah, the prime meridian, okay? The prime meridian means the number one, the uno, the one, the prime meridian. Let me run up and get the globe. I mean to bring it down here, but I didn't have time to go by the class. I'll be right. Let me pause this so you won't have a lot of dead time. Got it. Okay. Now, like I said, poles are here. Equidistance between the two poles, the equator. The equator is the beginning line for latitude. I'll read these to you if I can read. 15 degrees north, 30 degrees north, 60 degrees, 45 degrees north, 60 degrees north, 75 degrees north, 90 degrees north. Same south. 15 degrees south, 30 degrees south, 45 degrees south, 60 degrees south, 75 degrees south, and 90 degrees south, South Pole. That's your beginning point for latitude, is the equator. Goes plus or minus 90. But for the meridian, for longitude, there's nothing special about any one of those lines. So what do we use? The prime meridian. Where is the prime meridian? And why is it there? Any ideas? Say again?
Through Spain, right?
Through what?
Through France.
Okay, it does go through France, but the primary thing on it is, who was Queen of the Oceans? Great Britain, exactly. And Queen of the Ocean, those are the folks that use latitude, longitude the most probably. So they chose a spot where the Royal Naval Observatory was in Greenwich, England. Just a little bit west of London, I think. And that's why it's called, have you heard it, Greenwich Mean Time? Yes, that's where that comes from. Greenwich, England is where the Naval Observatory was, and that's where they said, let's make this the prime meridian. 0 degrees goes through Greenwich, England. And you're absolutely right. From Greenwich, England, it goes then, I may be wrong. It doesn't quite hit France, does it? Yes, it does. It has to go right through France. And, does it cut through Spain? Yes, it cuts a little bit through Spain, through Algeria, and down and down and down. So it's the prime meridian. All the meridian goes from North Pole to South Pole. It's the prime. 0 meridian. Prime usually means 1, but there it means 0. Okay? Now, just a little aside, has nothing to do with what we're doing, but my wife had professional meetings scheduled for, I think, Paris, and she decided to invite, can't remember who she invited first. I think it was a niece to go with her, and they've been wanting to go, but then the other niece found out about it. That was her brother's daughter. Her sister's daughter found out, so she wanted to go. And then when her sister's daughter found out, her sister wanted to go. And then when her mom found out that her sister was going, she wanted to go. And Karen said, how can I have professional meetings with all these people? So she just didn't go to those meetings, but she took her mom, her sister, and her two nieces to, and they actually did London and Paris. Okay? And what's that? I was here teaching. You think I would leave? Silly question. Okay, rhetorical. Never mind. Okay. No, it didn't work out. I have gone on some of the trips, but they have to be when I have a break. You know, she gets mad at me. No. Okay, never mind. But while they were in London, they decided to take a tour of the Naval Observatory in Greenwich, England. I wish I'd have been there then. But they got surprised when they were there. All these crowds were there, and they didn't think they were that important for them to come see them, but why were they there? And also saw a fair amount of security and stuff. Well, what's going on? They found out that the Naval Observatory was opening a new center or room or something, and the Queen was coming. And they got to see Elizabeth. They got to see her from a distance, but they got to see her do her little wave. Okay. So they got to go to the prime meridian, 0 degrees latitude, longitude. Okay. But then from here, you go east, and I'll show you on the globe too, if it's helpful. There's the prime meridian, 0 degrees, and they break them down into, they sort of do. 15 degrees, 30 degrees, 45 degrees, 90 degrees, 60 degrees, 75 degrees, 90 degrees. Do they stop there? No, they've got to go all the way to 180 degrees. So 90 degrees, 105 degrees, 120 degrees, 135 degrees, 150 degrees, 165 degrees, and finally to 180 degrees. I just went around east. You could have started back here at the prime meridian and go 15 west, 30 west, 45 west, 60 west, 75 west, and when you get over here to 90 west, that goes right up through, it's a little bit, well, almost smacks right through New Orleans, okay? Not quite, but close. It goes pretty close to Jackson, Mississippi. And so we're just a little bit, we're 80-something degrees west. That's where we live. And then it keeps on going around until you get to 180 degrees west, which is the same as 180 degrees east. Now, what is that line called? Over here at 180, see, we've been going, counting around east, counting around west, and what's that?
Tropic of Cancer.
No, the Tropic of Cancer's down here, up here.
Tropic of Capricorn.
That's down here. What's 180? It's a meridian line. Okay, now here's where this gets a little bizarre, but it's true. Okay? It's now getting close to 2, quarter till 2, 20 till 2 here. Is this the same time as it is in Atlanta? No. And if you keep going further east, you're gaining hours. And if you keep going west, you're getting, so say in Denver, it's quarter till 1. In Los Angeles, it's quarter till 12. And you keep going that way, and somewhere out there, these two times, this is today later in the afternoon, this is earlier today, what happens back here at 180? It's the same time there, but on one side, it's Tuesday, and on the other side, it's Wednesday. That's the international dateline. 180 degrees east or west from the prime meridian is the international dateline. When you cross that, you either gain a day or lose a day. Just like when you cross the time zone, you gain an hour or lose an hour. The international dateline, you gain a day or lose a day depending on which way you're going. So my wife got to go to Brisbane, Australia, in one of the meetings about a year and a half ago, almost 2 years ago now, and I can't remember which way it was. She left on a Thursday and got there on a Saturday, and coming back, she left on a Monday and got back on a Monday. I mean, it's just that you lost a day going one way and gained a day going the other way. And actually, I was on a ship in the Navy and crossed the international dateline a few times. And you know, it's funny. I never figured it out. On that ship, we always picked up, if we had it picked up a day, it was always a work day. But when we lost a day, it was always a weekend day. I never figured out how the captain came up with that, you know? But it always worked that way, somehow. What's that?
Maybe they were doing it just to mess with you guys.
I'm sorry, I'm hearing that.
Maybe they were doing it just to mess with you guys.
You better believe that's what they were doing. They were used to that. That was their specialty, was messing with us guys. Okay, so yes, you're absolutely right. You think like a commander. Never mind. We won't go there. All right, so there is longitude. Latitude, plus or you can say plus or minus, or 90 degrees north to 90 degrees south. Latitude. Longitude from 0 to 180 east, 180 west. So it's different numbering and different things. Okay. Okay, we've already done this part. So that's how we determine where we are on the globe. So many degrees north or south of the equator, so many degrees east or west of the international dateline. Okay, one of the labs coming up, not this lab, but on one of the chapters, which we really can't do a lab on that chapter, you'll do latitude and longitude. It's sort of a fun lab. Okay. I think we beat that to death. Okay. Now, position on the Earth is an intersection of the parallels. What are the parallels? Lines of latitude, and the meridians, those are lines of longitude. Okay, get those right. Parallels, latitude, meridians are longitude. Defined with respect to the rotation axis. There it is. The parallels are the latitude lines, meridians are the longitude lines. Now, here's just another little statement. Don't know how important it is to you. A circle that cuts through the globe, we'll assume the globe is a sphere. We know it's not quite a perfect sphere, but close. Okay, a circle that cuts through the center of the sphere is called a great circle. There's only one latitude line parallel that is a great circle. What is that? The equator, of course. All the others are getting smaller toward the top or the bottom. So they're not going through the center. How about your meridians or your longitude lines? Which of those are great circles? Every one of them. Because they all start at the North Pole, South Pole. They all meet up here. All meet right there and down here. They all meet there at the poles. So every one of them goes through the center. So every one of those is a great circle. Now, have any of you done any flying? Major flying, okay? Have you ever noticed the path that is taken? And I noticed it in the Navy too, on the ship, do the same thing. When you fly, say, from Atlanta, I don't know if that's where you fly from, to Paris, let's say that's where you're going, do you fly along, say, a parallel? No, you don't. That's the long way around. What you do, or what they do, is basically pretend to cut a great circle through the globe. And the great circle that goes through those two cities are here, that's going to take you up close to Iceland and Greenland. Because that's the great circle that connects those two. That's the shortest distance. So if you wondered sometime when you're on the transatlantic or Pacific or a long flight, why are we going so far north? That's the reason. Because you're flying a great circle route. Okay? And that's the shortest distance. Between 2 points on a flat map, that's a straight line. Shortest distance between 2 points on a globe, a great circle. Not a straight line, a great circle. Okay. That's neither here nor there. All right. Same slide we had before. The parallels go north from 0 to 90 degrees and south from 0 to 90 degrees toward the South Pole. This is the same one we had before. Don't know why they're repeating themselves. You pretend you had a protractor sitting across there and you're measuring the angle. 20 degrees north, 40 north, 60 north, 90 north. We've seen that one before. Okay? But they must think it's important. They showed it twice. Here's our longitude line. This is the one we didn't see before. These are 0, what is that one called? Nope, 0 longitude. Oh, how long ago? Which one? Prime meridian, that's it. 0 degrees, and then you go east or west. East is deeper into Europe and Asia and the Pacific there, and west is toward the Atlantic, U.S., North and South America, on into the Pacific that way. Okay? And then here is the same one we saw before. East, looks like maybe 30 degrees, 60 degrees. No, that is not a very good picture. That has that way too narrow between 90 and 180. The 90 should be out here somewhere. But anyway, it's just symbolic. Okay. Any questions? Identifying place. Now, there are some special parallels that are climate related. Parallels are which? Latitude. Some special parallels, climate related. I've already been asked about 2 of them today. 2 parallels that are climate related. Actually, 4 of them. 5 if you count one we've mentioned several times. Okay? They all have to do with the tilt of the earth. Yes, that's one. The Tropic of Cancer. Where is it? Say again? No, okay. Tropic of Cancer, remember these are parallels. Parallels go all the way around the globe, okay? So it's in the Pacific, of course, but it's also in the Atlantic and, wherever. Okay. It has to do with the tilt of the earth. Hint. Okay? It has to do with that. And there's another 2 parallels that are around the poles. Special ones. She mentioned the Tropic of Cancer. Where would it be? Okay, one's below the equator, one's above the equator. Which is which? Cancer's above. Capricorn's below. How far above, how far below? Has to do with the tilt of the earth. Okay. Say again? 23.5! Ding, 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 ding! Okay, yes. 23.5 degrees. 23 degrees, 30 minutes north is Tropic of Cancer. 23.5 degrees south, Tropic of Capricorn. Now, the other 2 I mentioned, I didn't say what they were. Where would they be? Near the poles. 23.5 degrees from the North Pole, which would make it 66.5 degrees north. or 23.5 degrees from the South Pole, which would be 66.5 degrees south. What are they called? Arctic Circle, Antarctic Circle. Exactly, exactly. Now, they're climate related. How are they climate related? What's between the two tropics? It's a trick question. The tropics, okay, because that's why we call them the tropics. They're in between the two tropics. And what do we call the ones that are up here and down here? Basically the polar regions, okay? That's the climate related. In between the tropics, you generally have warm weather, generally year-round warm weather. Around the polar regions, cold weather, round-the-clock cold weather. Colder in the winter than it is in the summer, but still, it's always pretty cold, okay? You can have snow any time of year in either place. There's more of it in the winter in each place. So, in between those, between 23, and where we live, 23.5 degrees north to 66.5 degrees north, that's called the temperate region, meaning in between the hots and the colds. Sure, we get hot in the summertime, we get cold in the wintertime, but we are temperate, kind of balanced between the two. So these are the special parallels that are climate related. And it all has to do with the tilt of the earth and the surface, how the sun sees our surface. Okay? All right. I guess we should start with summer. Okay, here, summer, here's the sun here in the middle, okay? When our North Pole is tilted as much as it can, 23.5 degrees to the sun, notice as you spin the globe, inside the Arctic Circle, the sun never sets. It's always lit on the 21st of June. Which day is that? Summer solstice, when the sun stands still. Solstice, okay? Now, on the Tropic of Cancer, on the first day of summer, the 21st of June, summer solstice, the sunlight is directly overhead on the Tropic of Cancer. Directly overhead. The only day of the year is directly overhead, Tropic of Cancer. Is the sun ever directly overhead in the temperate region? No. We get up to 80-something degrees, but never gets to 90. In the tropics, except for on the Tropic of Cancer and the Tropic of Capricorn, the sun is directly overhead twice a year. It'll vary on different days, but it's always twice a year. Like, it'll be directly overhead. It was a little bit before this, at this point, and then after this a little bit, it'll be directly overhead again when it gets a little bit tilted away, okay? On the equator, guess when it's directly overhead? Spring and winter, and fall equinox, you're absolutely right. That's when it'll be directly overhead on the equator, okay? And Tropic of Capricorn, when it's directly overhead? Around, it is not a solstice. Yeah, it is, you're absolutely right. It's our winter solstice, which is their summer solstice, okay? That's when it's directly overhead there. That's summertime in the southern hemisphere, but it's our winter solstice. But in between, everywhere in the tropics, the sun is directly overhead twice a year. On the tropics, Cancer and Capricorn, directly overhead one day a year. So, but always it's close to being. You get a lot of sunlight all year round, okay? In the temperate region, it's never directly overhead. In the polar region, it's nowhere close to being directly overhead, okay? It's just barely up sometimes, okay? Now, in our summer solstice, what's happening inside the Antarctic Circle? 24 hours of darkness. And the closer you get to the South Pole, or later the North Pole, the more days that it's total darkness. But on the Arctic Circle, only one day is total darkness, and that's the summer solstice down here, winter solstice up there. Okay? Does that make sense? That's why they say they're climate related, because warm all year round, you have 4 seasons in the temperate region, and it's cold all year long in the polar regions. Winter solstice, everything's reversed. Now the South Antarctic Circle, total 24 hours of daylight, 24 hours of darkness at the North Polar region. The sun is directly overhead, Tropic of Capricorn, on our winter solstice, which is their summer solstice, okay? And it's as low as they'll ever get for anything north of the equator. Does that make sense? All right. Here we have, here my pen. Terry, right? Okay, Terry Wright. Ah, got it. Okay. All right. He must have thought I was going to be a long time at the doctor's office. Okay. All right. Any question on those special parallels? There's actually 5 of them. The equator is a special parallel. It's the only parallel that is also a what? Great circle. Goes through the center of the, all the other parallels don't go through the center of the earth. Okay. All the meridia go through the center of the earth. They all form great circles. Okay, this isn't talking about. Okay, now let's talk about time. We've already been hinting on time. Time standards depend on measuring the intervals between evenly spaced periodic events. We did this in the last lab, I believe. Okay? Astronomical examples, okay? And I remember someone asked a question, it was a great question, and I got to thinking later that I really answered it the best I could. And somebody said, why is it a fraction of a day? Why do we have to have a leap day? And I hope I answered something like this. Our days are determined by 1 complete rotation of the sun, of the earth, right? Our year is determined by 1 complete revolution around the sun. Right? Okay. The earth doesn't keep up with how it's going around the sun. It has a fraction of a spin left over. Okay? It doesn't fit exactly. So it spins 365 and then a little bit more. Not quite a quarter of a spin by the time we go all the way around. That's why we have a leap year. Okay? About every 4 years. Except for every 4th century, we don't have a leap year. Okay, so we talked about that. Okay, so it's a combination of the rotation of the earth, which determines what? Rotation of the earth? Our days, okay? Revolution of the earth around the sun determines our year. Now, so we got the basis of the day, the spin, rotation. Okay, we didn't do month yet. The year, that's the revolution. How about this month and season?
Probably how close and how far away we are from the sun.
Say this again.
How close and how far away we are from the sun.
Okay, that's certainly a part of it. It's not so much how far we are, but what our tilt is rather than the sun. So the seasons are determined by the tilt. Okay? If you think about that. What are the 4 deciding intervals? You've named them all 4 already today. Okay, those are the seasons. What is the thing that makes the divide between those seasons? That makes the divide, say, between spring and summer. The solstice, yeah. You have 2 solstices, summer solstice and winter solstice, June 21st, December 21st, or something about like that. And the 2 equinoxes, those are the ones. So if we're between the vernal equinox, which means spring equinox, and the summer solstice, we're in spring. If we're between the summer solstice and the autumnal equinox, we're in summer. If we're in between the autumnal equinox and the winter solstice, we're in the fall, autumn, and we're between the winter solstice and spring equinox, we're in winter, okay? That it marks the beginning, okay? So that's what determines the seasons. We haven't said anything about months yet, okay? I'm going to ask for your a little bit of imagination here. If I wipe out the TH and ask you to put in one extra letter, what do you see? Moon! The month is determined by the moon. That's where it gets its name. The moon. Okay? Only we misspell it. Okay. All right. And there are different ways to measure days, months, and years. We talked about days and years, I think, in the last lab, didn't we? Sidereal day. Oh, and I think it's the upcoming lab. Today's lab, I think we'll have time to do it, is when we'll talk about those different ways to measure days, times, days, months, and years. Please read the book. Please read the book. A lot more here than I can go over in class. Okay? So let's look at daily time. That's not the same as this is on page 415 or thereabouts. The daily time determined by the Earth-Sun motion. If you look down from the North Pole, if you were way up here in space, and look down from the North Pole, which way does the Earth turn? Do you know? If you're looking at the North Pole, say again? Did I hear clockwise or counterclockwise? Counterclockwise. Believe you're right. It turns like that. And how do you know that? The sun rises in the east and sets in the west. So yeah, it's turning counterclockwise. Of course, if you're looking at it from the South Pole, it's turning clockwise. So it just depends on where you are in space to see. Oh yeah, and it's here on the slide too. Thank you very much, reading it very well. The Earth revolves from the North Pole counterclockwise around the sun. Now wait. Okay. Get this. Okay. It rotates counterclockwise, but it also revolves. If you're above the North Pole of the sun looking down, we're going around the sun in a counterclockwise motion. Okay? So it both revolves around the sun counterclockwise, and it rotates counterclockwise around the axis. Now, therefore, you have the sun rising in the east, setting in the west. It's not really rising and setting, we're spinning, and that's where it looks like it comes up and goes down. Okay? Does that make sense? Now, because of that, now remember the last thing on the last slide, we were talking about different ways to measure to measure time, days, and years, and that kind of stuff. Well, here's why. And you've seen this on the lab, I think, the last lab. Okay? Let's say that at a given day, we're here. Okay, and we're right there. Sun's directly overhead, and we're spinning counterclockwise, and we're going around the sun counterclockwise. Okay? So that day, we spin counterclockwise. But while we're spinning, we're also moving through space, remember? Around the sun. We go about, remember, it's about 1 degree around the sun. Now that's certainly a lot bigger than a degree, so this is several days, okay? But it says one. I must way too much. Okay. They say 1 day later. This is an exaggeration. That's a really big degree there, okay? 1 degree later, 1 day later, when we go around the sun, where we were here, 1 spin later, we're right here, but the sun's not directly overhead yet, is it? It was directly overhead this day, that's our noon, but up here it's still morning. We got just a few minutes to go before we get down there. So that's why our solar day is longer, about 4 minutes longer than a sidereal day. What's a sidereal day? Well, let's just say at this time you were over here and you were happening to look at a star out there. Directly overhead, crossing your meridian, high as it's going to be, or whatever, you know. And 1 sidereal day later, it's right there. But that's shorter than a solar day because the sun has to spin just a little bit further. The Earth has to spin just a little bit further to get to a noon, another noon. So that's why a solar day is longer than a sidereal day by about 4 minutes, approximately 4 minutes. Okay? Does that make sense? That's why there's different ways to measure the day. Solar day, that makes sense for us. Sidereal day, only if you're a vampire and never saw the sun, then maybe that makes... I didn't say that, did I? Okay. All right. So let's look at the sun's motion across the sky. Is that... Yeah. Now, we haven't quite gotten there yet, but there is an example, 16.3, how many sidereal days are in 1 year. And that's a fun problem to look at and read through. I won't go through it in class, especially since we lost so much time today because of my doctor's visit, but it's really a fun problem. Take a look at that, see if you follow it. Okay, we're moving on from that to sun's motion across the sky. What do we call our noon? Again, in this room, I get sort of crossed up. Let's see. Trying to picture in a classroom up there, Vesper Superhighway goes sort of like this, doesn't it? Vesper Superhighway is kind of going north-south, not exactly, but close to it. So I'm going to say that's due north. I think I'm right with this, and this is due south, just to have some place. Huh? Okay, you got a compass. Okay, so that's north. Okay, I was doing the highway. The highway isn't true north and south. Okay, so here's due north, and there's due south. Okay? Now, that makes due east over here, due west over here. Now, if we're facing due south, okay, what's the line that goes from due south through our zenith and to due north? Our local meridian, that goes through the poles, right? Meridian goes through the poles. So, when we're looking at the sun here, at the moment when the sun crosses our local meridian, that technically is our noon. That is our noon. Noon is the time at which the sun is at the celestial meridian, crosses celestial meridian. Highest point the sun will go in the sky that day. Now, they call it apparent local noon. When I was in the Navy, we called it local apparent noon. I don't know why the difference, except that now LAN stands for Local Area Network, so I guess they don't want to confuse themselves with computer terms. So they say apparent local noon. And that's always at a particular longitude. Where you are, that's where it is. That's never really when noon is. Remember, we talked about this in the last chapter. Remember, if we put covered the windows completely, blackened them completely, left a little circle there, and we marked that local noon on the floor where the sun came through that at noon every day, what would we form? A figure 8. What do we call that? Analemma. That was the analemma, that figure 8. We'll go into that in a little bit later too. All right. Now, the apparent local solar time would then, given that position of the sun in the sky, what time would it be? Can be measured with a, I don't know how to pronounce that, gnomon, I guess it is. The G, I think, is silent. Or a sundial. I like sundial, okay? But actually, your figure 8 is another form of the sundial. It's just measuring days of the year. The sundial is measuring hours. Okay, that's not the time you'll see on clocks, except very rarely, maybe 4 times a year it'll be pretty close to true. And that's about all. That's 4 times it crosses local apparent noon. Okay? So, what do we do? Sometimes the sun is, and the reason is, remember, when we're going around the sun, we're changing speeds. When we're closest to the sun, which occurs about what day of the year? closest to the sun around January, around January 4th, something around in there. That's when we're closest to the sun. That's when we're moving the fastest. So the sun seems like it's moving faster, okay? When the farthest from the sun would then put us, what month? July, early July. And that's when we're moving the slowest. When we're moving slower, as you stretch out that figure 8. One part of the figure 8 is tight. The bottom part is pretty big. That's why that happens. So what we have to do is average all those days and make that the time average from apparent solar time every day, average that over the whole year, and that gives us our mean solar time. Mean means average. Doesn't mean you're ugly and nasty. Okay, it does mean that, but I mean, when my wife tells me I'm mean, I say no, I'm just below average. So she doesn't like that. Okay, all right. It's averaged over 2 effects. We just mentioned 2 of them. Number 1, the Earth's orbital speed changes throughout its elliptical orbit. Right now we're slowing down. We were at our fastest early January, ever so slightly slowing down, but we're still moving pretty fast, okay? When we get along about early April, we'll be close to our average speed, and then when we get over in July, we'll be at a slowest speed. So the Earth's orbital speed changes throughout its elliptic orbit. Second thing is the equator is inclined to the ecliptic, okay? Which also sort of adds some confusing things to it, okay? So what is a mean solar day? It's a 24-hour average of the mean solar time. You do the mean solar time every day of the year, average that out, and you get the mean solar day. Make sense? All right. So what is a day? Length of time for the Earth to rotate once on its axis. No, that's a sidereal day. You need a little bit more to give it a solar day, okay? Sidereal day is one time around the axis, the interval between 2 consecutive crossings of the celestial meridian by a particular star out there, not by our sun, not by that star. Little variation because of the Earth's constant rotational rate, that's pretty constant. But the apparent solar day is the interval between 2 consecutive crossings of the sun's over our celestial meridian, which has that extra 4 minutes or so for us to turn a little bit further because of the distance we move around the sun. Imagine figuring this out for Venus. Venus is spinning backwards, but going the right way around the sun. Oh my word, how do you figure out the days and times there? I'm glad I don't live on Venus, besides being in sulfuric acid. I don't know.
The way to drive with this is crazy.
What's that?
The way to drive with this is crazy.
Yeah. Now, how about Uranus? It's almost sitting on its axis spinning. Yeah. Hang that one up, okay? I'm not going to go there anyway, so I don't have to figure that out. Okay. So, apparent solar day is the interval between 2 consecutive crossings of the celestial meridian by the sun, not by a star, and because we have to go a little bit further, it spins a little bit further. The revolution about the sun changes the Earth's sun orientation every day, okay? It's about 4 minutes longer than a sidereal day. That's the important thing. So, why they put this here, that should go over there. 23 hours, 56 minutes, and 4 seconds is a sidereal day, not a solar day. A solar day is closer to 24 hours. Mean solar day is 24 hours. That at the bottom should be under sidereal day. Sorry about that. Who put these together, I do not know. Make sense? Okay. Now, this chapter calls it the equation of time. Okay? This is along about page 417 or so. It depends on which edition you have of the book. This is another word for analemma, the equation of time. This traces the yearly variations between the apparent local time and the mean solar time. Okay? There is the path of the sun at a given time every day of the year, you might say. When the sun's right up here, you know what that's called? Highest it's going to be? It's what?
Zenith passage. Zenith passage.
One more.
Zenith passage.
Oh.
Zenith passage.
Venus.
Zenith.
Zenith.
Oh, zenith. Okay. Okay. Somewhere, yeah, that's directly overhead. But what I'm meaning here, what is this line here where the sun is directly overhead on when it's highest in the sky in the northern hemisphere? Where would that be? How many degrees north of the equator? 23.5 degrees, okay? And what is the line that's 23.5 degrees north? Tropic of Cancer, yes, okay? The equator is down here, okay? And then when the sun's lowest in the sky, in the northern hemisphere, which is highest in the sky in the southern hemisphere, where is it then? (23.5 degrees south, which is the Tropic of Capricorn. You got it. Okay. So, the sun's directly overhead everywhere on the Tropic of Cancer 1 day a year. Just 1 day a year. That's in Mexico, just north of Cuba. Cuba is totally in the tropics. Florida is just out of the tropics. And what's that, 90 miles between? So it's not far. And cutting through, I think this is probably Algeria or some of those countries in Africa, probably a little bit of Egypt here, Saudi Arabia, India. I guess China goes down that far. That's Tropic of Cancer. Tropic of Capricorn goes down. Certainly some of Brazil is in here. Some of Argentina, Peru, I'm thinking is here. Or is that Chile?
That's Chile.
That's Chile down here. It's Chile further south. I'm sorry.
Chile's like right below.
What's that?
The Chile's right below Peru.
Further down. Is that what you're saying?
No, you had it right.
Oh, it's right about there?
Yeah.
Okay. It's right on the coast, I knew. And Peru is, I think, a little bit north of that. Okay. So anyway, that would be Chile and Argentina and Brazil. And then this looks like mostly South Africa, possibly Botswana and Namibia or some of those countries there. This is the Madagascar and Australia. About half of Australia is in the tropics, the other half is in the temperate region. Sydney's down here, Melbourne's over here, Perth, I think, is over here. Brisbane is a little further north here, and up here, I can't think of those towns, but the Great Barrier Reef is up here, so that's in the tropics there. So, anything in between those are the tropics. The sun is directly overhead once a day on the tropics, Capricorn and Cancer, twice a day anywhere between them. I mean, twice a year, anytime between them. It's like it would be directly overhead when the sun's here or when the sun's here. As the Earth's spinning directly overhead twice there, certainly the equator twice, and down here twice. These will be closer together longer before the next two. Equator equally spaced. Okay, so that's it. Now, that's just part of the picture. If you also sort of bend this over in itself, you almost get a figure 8, but that's not quite the figure 8 we're talking about. Okay, let's hit the rest of this. Let's see if I can get the figure 8 to show up. This shows a little bit better the clock before the sun is shown on the sundial, so many minutes before, so many minutes afterwards. If you took this one and folded it on the center, okay, did you hear the sound effect? Okay, never mind. But then you would have your little part of the figure 8 up top, the big part at the bottom. That's your analemma, the figure 8. It doesn't show it. Why won't it show it? I don't know. Okay. I don't even think it shows it in the book, but it's on the lab that we did last time. Okay? They talk about it, appears as a figure 8 on the floor. If you trace that out, you get that. The two effects, the axis tilt was one of them. That's the north-south stretching of the figure 8. The orbital speed, that's the east-west, whether it's skinny or fat. Okay? That's the east-west deviations. That's called the equation of time, or the analemma. It's the cumulative plot, just like we saw in the lab. It shows days of the year, declination of the sun, minutes ahead or behind clock time. All those three things are on that one graph. Okay. Believe we're ready for, and the best I can come here is imagine folding this over that point right there. You get your figure 8. This folds over here, this folds over there. There's your figure 8. And that's basically how they do it. Because remember, the minutes ahead or before clock time, those are vertical before. Okay? So yeah, that's it exactly. All right, now let's talk about the standard time zones. Okay? This is beginning around right at the end of 417, beginning of 418, or thereabouts. Your book does have it. I found it. On page 417, the figure 1621. My guess is it should have been right there, and they just didn't show it. I don't know why. But it's on page 417 or thereabouts, figure 1621. Now, different editions of the book may have the figures different and the pages different, but it should be in there. All right, so let's think about the equation of time. Okay, no, we already did that. The standard time zones. So what we have, how many degrees have we got around the circle? 3, all the way around. 360. 360 all the way around. And how many hours does that represent in the day? 24. Divide 360 by 24, and you get 15 degrees each time zone. So let me sort of show you what that looks like. Basically, that's 15 degrees. Let me get the 15 degrees closest to us. Right there. It's sort of tough to do right here, between 75 degrees west and 90 degrees west. 15 degrees, that's us, okay? Now, really, Maine should be in the Atlantic time zone, not the Eastern time zone. But to keep it inside, they move it down. Actually, New York City should be, well, I take that back. Sorry. They centered these on the degrees. If you centered the 15 degrees on 75 degrees, that would be 7.5 degrees east and 7.5 degrees west. So then Maine, still part of Maine should be out, but that should be the Eastern time zone. Now all of Georgia would not be on it, but to keep all the state together, they squeezed it in there. The center on the 90 degrees, as I said, that's Jackson, Mississippi. We're where we belong, but we're in the eastern part of the Central Time Zone. So in many ways, we're more like, or similar to the Eastern Time. Okay. They say it's adjusted for local consistency. What does that mean? Keeping as much as possible countries or states within the same time zone. Now some can't be, okay? Let's see the picture of it here, okay? As you see, it's probably hard to see here. It actually looks like it should be different, but from what I was just pointing out. See, Maine should be, the tip of Maine should be in the Atlantic time zone, but it's very little of it, so they pulled that into the Eastern time zone. Now, the other edge here is here. Tennessee is such a long state, and it's Eastern Tennessee feels more like North Carolina and Georgia. Chattanooga is so close to Georgia. They want to be on the same time zone. Memphis is just north of us. Nashville just north of us, so they went on Central. Memphis, of course, will be on Central. So Tennessee and Kentucky had to split. And really it gets down to local consistency. This part of Kentucky is more like that part of Tennessee, so they get on the same. This part of Kentucky is more like Ohio and Indiana and West Virginia, so it gets on that time zone. Now, unfortunately, a little bit of Indiana got over here, and most of Indiana's up there. Look what they did to Michigan. You know, Michigan is separated. This is the UP. Does anyone know what they mean by UP, Michigan? Upper Peninsula. It's not at all connected to the rest of the state of Michigan. You have to get to it by water, okay? So the Upper Peninsula, even though that should be Central Time Zone, they made it part of Eastern just because the rest of Michigan was Eastern. Texas, and this is mostly just for local consistency. I think Santa Fe, New Mexico is the biggest city in this area, and this part of Texas feels more like they go there for their groceries. You know, they don't come to Dallas or somewhere so much closer, so they go with that. Same thing with Kansas. I can't think what part of Colorado is that. Boulder and, see, Denver's up here somewhere, I think. So this part of Kansas feels more like Colorado, so they went with those. Same thing with Nebraska. People in this part of Nebraska go to Lincoln and Omaha. This part they go over to Denver when they go to the big city. So they get on that time zone. South Dakota is not close to anything, so you just split the state in two. But they kept counties together. That's why you have the Jigs and the Zags. And North Dakota did sort of the same thing. Poor old Idaho got chopped up. Northern Idaho is more closely related to Washington, so it went Pacific time zone. But Southern Idaho, I guess they felt more like Salt Lake City in those areas, so they went Mountain time zone. Rather strange. Local consistency. Okay? Why in the world they did this? Look how narrow the Mountain time zone is there and how big Central time zone is here. That's just because Mexico really did a strange thing down here. The U.S. didn't do it, but Mexico did. They went way over here before they ended the Central time zone. Rather bizarre. Okay? But that's how that works. So, basically about 15 degrees each time zone, but adjusted for local consistency. Now, I don't know what y'all feel about it. I do not like daylight saving time. Y'all probably love it, don't you?
I don't like it.
Okay, I don't either. What's that? You do like it that way?
I like having more daylight.
Yeah. That's why they do it. Most people did. Are you a golfer by any chance? No, okay. I figured all the executives, you know, the honchos, you know, the CEOs and stuff wanted to play more golf in the evening. I thought that's the reason they did it. But I've been told, no, it's the farmers. The farmers don't really care, I don't think. I knew dairy farmers, guess what? Their cows need to be milked twice a day, and they don't care what time it is. They want to be milked. You know, their bags are heavy. They want to get relief. So they have to adjust the times, you know. Sometimes they're going out at 6 in the morning. Sometimes they're going out at 5 in the morning because cows don't care. They just want to be milked, okay? So I don't think it's necessarily the farmers, but who knows? Maybe those who have kids in school, they want them to be able to work in the field a little longer when they get home in the summer. I don't know, or spring or fall. But anyway, daylight saving time, clock set ahead in the spring, spring ahead, and back in the fall, fall back, okay? For an extra hour of sunlight during the summer evenings in the spring and summer. Okay. We're in regular time now. I like it better. Okay. Well, here's what I especially don't like. See, we had to catch the bus out in the farm when I was in school, and when they set that clock in the springtime, I mean, it had to be out there to catch the bus at 7, you know, to get to school by 8. And in the fall, that was getting later, and I mean, the sun was coming up later and later, so it was getting darker and darker, and stuff. Let's go around to the spring. We just were beginning to get a little bit of light at 7 o'clock. It was being bearable. And then all of a sudden, they set the daylight saving time. We're back in the dark again. I hated that, to be down there. And then at football practice, the coach thought we could keep it out there later if it had more daylight time. So I didn't like that either. Okay, never mind. That's the side. Okay. International Dateline, that's the 180-degree meridian. We already talked about that. It's designated to correlate days with the 24-hour time zone. Also, going around one way and the other way, you get to the same time but different days. Okay. Now, I'll tell you a dumb story. We talked about the time zones making a difference. International Dateline does too. Okay? I don't know if you'll see this. I think I'll turn on the light just briefly on this one. In fact, this may even be in the slide. Let's see if it's in the slide. I think it is, now that I think about it. Yeah, there it is. Okay, I won't need this. Now, the international dateline should be the 180-degree meridian. This is 180 degrees east, this is 180 degrees west, 180 degrees, 180 degrees. Okay. But part of Siberia sticks over into the previous day. And that's part of Russia, used to be the Soviet Union. They didn't want to split it on a different day, so they inched it around. But then the Aleutian Islands belong to this island, Ark Islands here off Alaska, that's part of us, and they wanted them to stay with us. So it jigs over here to the east to include Siberia and the other side, and then jigs back to the west to get all the Aleutian Islands on our side. Okay? And then it goes pretty much straight down until you get down here. New Zealand, you see down here, is awfully close to 180 degrees. We actually has a few islands out here that belong to New Zealand, and they wanted to stay. And these other islands relate to Australia and New Zealand, so they wanted to stay, so they jig it out here again for local consistency. Now, here is a story I heard in the Navy. You're not going to be tested on this one, but because Navy stories shouldn't be on a test, I don't think. But supposedly, there was an island somewhere in the Pacific that the international dateline cut right through, supposedly. And some entrepreneur decided to build him a bar right on that island, on the international dateline. Why? So when it got to be Sunday morning on one side, it was Saturday night on the other side, or Sunday night became Monday. So he could always, on the Sundays, he could close half the bar and keep the other half open. Not that the Navy would mind that would care about that at all. Okay. Say again?
It's actually a pretty good idea.
Yeah, okay. All you had to do was move across the line and you could keep on. Never mind. We won't go there. Now let's look at yearly time. Okay? Now this is on page 419. Before we do that, there is a blurb at the top of page 419. And this is about what we're just talking. Is daylight saving time really saving any time? No. I mean, you still have 24 hours in a day. It's just one day in the spring. You have an extra hour, and one day, is it the other way? In the fall, you have the extra hour. In the spring, you lose an hour. And here's the other thing that hacks me off about it. In the spring, when you turn the clocks up, you lose that hour. They always do that at 2 a.m. I hate getting up at 2 a.m. and setting my clock. No, I'm just kidding. I don't do that, okay? Not even anal retentive of me does that. Okay. But I always stay up till the same time, but then have to get up an hour early. Now you might say, but you get it back in the fall. No, you don't. That day I stay up an hour later and get up. I never get that hour sleep back. Never. Yeah.
I'm insomniac and daylight saving time, please. Oh, my schedule. by the time I get used to not having
Yes.
to get up this early, I have to.
You have to do it. I hate that mess. I do.
So
I really
I feel
do.
like a zombie.
Yes. Exactly. So, not only are there two different days, what are they, by the way? Solar day according to the sun and sidereal day according to the stars. There's also two different years. And why they don't use solar? They use sidereal, but they don't use solar. They use tropical year. Okay? That's the interval between two consecutive spring equinoxes. That's made up of the Earth's rotation around the sun. You know, spring equinox is when equal day, equal night. That is 365.2422 mean solar days. Not quite a quarter of a day. So, but we do add a day every 4 years, so we get a little bit ahead, but then every 4 centuries, we don't add that day to make up for these extra decimal places here. The sidereal year, however, is the interval between two consecutive alignments of the Earth and the sun relative to the stars. It, strangely enough, is 20 minutes longer than a tropical year. 20 minutes. 20 minutes in a year, that's not very much at all. Okay? Little bit of a difference there. Now, how do we account for this? Adjustments to keep calendar years current with the seasons. You can either put in leap years. That's what we do. Every leap year, every 4 years, we add an extra day. Because this is almost a quarter of a day. 2 would be almost half a day. 3 would almost be 3/4 of a day. And 4 would almost have been an extra day. So they put the extra day in on February 29th. But some people have suggested, why don't we have just leap seconds? In other words, just when it's time, just add an extra second. No one would ever notice, okay? But of course, how do you keep up with that anyway? So, no, we keep the 24 hours mean solar day and do a leap year every 4 years, except every 4 centuries we don't do one. Okay. Now we're getting to monthly time. Okay? What does monthly time depend on? The moon. Not the sun, not the stars, but the moon. But still we have a sidereal month, which guesses what it's based on? Stars. And then why don't we call it a solar month or a tropical month? No, have a different name. A synodic month. Okay? Ooh, what is going on here? Well, the sidereal month is the one based on the stars. It's the orbital time measured with respect to the stars. In other words, the moon goes around the Earth, orbits around the Earth, one time in every 27 1/3 day. However, the synodic month relative to the sun, you don't want it to just go around the Earth once because the Earth is moving. The moon has to catch up then, and that amount it has to catch up, you see, this would be between a full moon here and one time around the Earth, it wouldn't quite be full. Not quite. You have to go up here to be full. That's what a synodic month is, between full moon and full moon, or new moon and new moon, whichever. But between the stars, here's the Earth. Say there's a star out here, way out here, not the sun, but some other star. And when the moon is lined up there, and the next time it is, that would be a sidereal month. But it's not according to the phases of the moon. So the time interval between two consecutive phases, which lines the sun, moon, and Earth up, that's going to be 29.5 days. That's close to our average month. Not quite, but close. Okay? So, why don't we have our months as all 29 or 30 days? We have most of them 30 or 31 days, and then one that's 28. Where does that come from? I don't know. I don't know who made those decisions. But, you see, you got another issue here. Just like the Earth doesn't spin exactly 365 times as it goes around the sun, it spins a little more. Well, the moon's orbit around the Earth isn't exactly in keeping with our orbit around the sun. So that's why it gets off a little bit. Who came up with the 30 and 31 days and 28 days? I don't know. Might be a good paper topic if that's what you're interested in. So, again, if you see the word sidereal, think twinkle, twinkle, stars. If you see the other words, solar, that means sun, tropical year, that means sun, and synodic month, that's when they refer to the sun. It's phases of the moon, but that's when it lines up with the sun. We'll talk about that more in the next chapter. Any questions on that? Okay. I'm sorry, it's this chapter. Duh! I keep thinking I'm a chapter behind. This is the chapter we talk about the moon. That's why it was in there. That was a good segue to get between the earth and the moon. So let's talk about it. The moon. The moon is our one and only naturally occurring planet of the earth, you might say. It's our satellite. Our naturally occurring satellite is the moon. It's on average about 380,000 kilometers away, which would be about 190 to 200,000 miles away. Okay, something around in there. Now, the moon is characterized by craters. What would it cause them? Meteors crashing into it. Why would they form craters there? Don't we have meteors crashing into the earth? Not many. Why? Say that again? Yes, we have such a nice, friendly atmosphere that burns them up before they crash into it. The moon has no atmosphere. Okay? Now, so the whole moon's covered with craters, but there's two other parts. The lunar highlands, sort of like mountainous regions, and Maria, which are ancient lava flows. You see, the moon used to be seismically active. In other words, had volcanic activity on it. And they had lava flows. Now, why were they called Maria? Maria? No, not that. Okay. They were called that because of M-E-R, myrrh. When they first looked at it, they thought the dark areas were water. Oceans, seas. And myrrh means sea. Okay? So they thought it was water. It's not. They were ancient lava flows. We know now. Basically, no atmosphere. That's why there's all the craters there. We've been to the moon. Now, maybe not landed on the moon, but we've been to the moon 12 times. 12 Apollo missions. Now, does that mean there were only 12 Apollo missions? No. We had several Apollo missions that didn't make their way to the moon. They were practicing and doing all the things, but they didn't actually go there. Why? There's one real famous Apollo mission that's outside of 12. Lucky number 13. What happened to Apollo 13? Yeah, it was the one that almost was a big space, well, another space disaster. Okay? We had the space shuttles, well, we had several, okay? But the Apollo 13 was on its way back, and they basically had a leak or something, and they had to get into the command module and fly it back that way. Not the best way to go. Very cramped. And they made the movie. Tom Hanks. Opie was the director of it. I can't think of his name. Ron Howard was the director. Another pretty famous actor was in it. I can't think of his name right now. But that was Apollo 13. That was one that did make it, made it to the moon, but I don't think they were able to carry out their mission. They had to abort and come back. The famous line that came out of that, does anyone remember? Houston, we have a problem. Yeah. So Houston, we have a problem. All right, there is a sort of a composite picture of the moon. I kind of assume this is one of the poles of the moon. I'm not sure if that's really true, but I think it may be. These are some, you see big crater areas and smaller. These are probably the Maria here. These are the highlands in white. So lots of craters. Now, some pretty interesting facts about the moon. We've already mentioned several of them. Okay? If we don't get to them on the slides, I'll try to bring them back up again. Anyone know what about 3 meters is? Okay, 9 feet. Very good. Okay? So if I stand against this wall here, I'm about 2 meters tall. A little bit less than 2 meters. So the other half of that. So it's basically about to the ceiling, approximately. Okay? So that's about 3 meters. 3 meters of fine dust on the surface. What does that mean? If you were to step on it, you might just, if you especially had on spike heels or something, you're going to go down, okay? Yeah, you might get covered with it because it's 3 meters of fine gray dust. So basically astronauts had things that looked like almost snowshoes on, so they wouldn't sink into the fine dust. Now, where is that from? Accumulated from micrometeorite impacts. They've just been hit by so much space junk over so long a period of time. It's just, and there's been pretty major collisions, it's just beat it to death. Now, some of that is from the fact that when those things hit at such high rates of speed, a lot of heat is put off, and actually the surface melts and then rehardens. So it becomes glass beads formed from the melted material rehardening, okay? Because things tend to go in spheres, okay? The rocks are basically basalts. Now, does that mean anything to any of you? Next chapter it'll mean something, okay? They're what? Yeah, they're basically volcanic. They're high iron content. They're usually very dark, formed from molten lava. There, I think you read the next line, yeah. No, I'm just kidding. No, that's exactly right. Basalts on the earth are mostly under the sea. Not always. There are some basalts in dry land, but they're from rapid cooling of molten lava. The light-colored highland rock, that's what I was saying before, we think were formed about 4 billion years ago. The dark-colored Maria rocks range from 3.1 to 3.8 billion years old. So they think the highland rock, the light-colored highland rock, formed first, and then you had the seismic activity where you had the volcanic activity going on, and those dark-colored Maria rocks range from about 3.1 to 3.8 billion years. Okay? Close to that 4 billion. Hang on to those numbers for a bit. The internal structure of the moon. Okay? So you have 3 meters of fine gray dust on the surface. Then you have from 65 to about 130 kilometers of outer rock. Now here's the first of these interesting facts. The 65 meters thick of outer rock is toward the Earth. The 130 kilometers of outer rock, that's on the back side of the moon, the far side. That's not the cartoon strip, but it's close to it. Okay? Now, that leads to something else. Okay? Here we are. Yes?
Doesn't this class have to be out of here by 3?
Okay.
Don't you guys have to be out of here by 3?
You have to be out by 3 is what you're saying?
No, this class.
Oh, yeah. It comes, I think that next class comes at 4, but we usually go at 3. Is it closer? Yes, it's awfully close to 3. Okay. Yeah. If I had been here 45 minutes earlier, we would have finished the chapter. Are we going to finish in the next 10 minutes? Okay, we're right now on page 421. Okay. Yeah. All right. Don't think it's going to matter that much. Do y'all want to go on and have the lab today, even though we haven't quite finished the chapter? I think we've covered enough to cover the lab. And then next time, we will finish this chapter and get started on the next one, unless we won't be going to the planetarium next time anyway. So we'll get started on the next chapter.
You want to do the lab next time, since so many people are not here?
Well, the thing is, we'll already be into chapter, in 2 hours, we're going to get pretty far through the next chapter, and then we'll have the test at the end of that. So if we wait and finish the chapter, then they'll at least hear the end. I don't know. Y'all are here. I want to do what y'all would like to do. Would you rather have 2 more hours of class or stop and have a lab?
Doesn't matter to me either way.
What you think? You raise your hand?
Yeah, 2 more hours.
You rather do all and do?
Because not that many people here.
Okay. All right. That's what you want to do?
But we'll have the test on Thursday?
Yeah, we'll do the lab for 2 hours and the test will last 30 minutes. Okay, because we'll definitely finish the class in those 2 hours easily, because we haven't been here 2 hours and we almost got it through. Okay, but here's the deal. We're going around the sun, remember? We're spinning, remember? Okay? Now, we're spinning and going around the sun, but at the same time, the moon is going around us. Here is the strange feature, and they're going to mention it later. They sort of suggested it here. The moon always faces the Earth the same way. In other words, one revolution of the moon around the Earth is the same period as one spin of the moon. Okay? That is strange. Now, number 2, remember we already mentioned this. We have the biggest moon relative to our size of any of the planets. Mercury has no moon. Venus has no moon. Mars has a couple little bitty rocks they probably picked up off the asteroid belt, but it got too close. And then the gas giants have umpteen moons, especially Jupiter has close to 50 or more. Saturn seems like close to 20. And then Uranus and Neptune have several. But they're way out there. Why do we have such a big moon? There's only probably 3 to 5 moons in the whole solar system as big as ours, bigger than ours. Our moon's almost the size of Mercury. It's bigger than Pluto. Why is our moon so big for us to be such a small planet? Here is a theory that something collided majorly with the Earth sometime in our distant past and broke off the moon. And therefore that piece that was out there was already going at the same speed as the Earth, and that's why it never spins. It spins once, but it's always facing us. And that's why the far side of the moon is always the far side of the moon, because it's always out there. And if it broke off from us, then that would make sense. The thickest piece would be out there, the thinner piece toward us. Interesting. We can't, I don't know if there's any way you'll ever prove that's happened, but it sure looks like it may have. Okay? So, 900 kilometers into the moon, okay, you get a partly molten iron core. That means not quite all liquid, but mostly liquid. Partly melted iron core. And that's just because of all the gravitational pressure that's on it. It's hot enough to melt the iron. Okay? And that's where the old volcanoes came from. And if you think about it, if that light-colored highland rock was formed about 4 billion years ago, maybe that's when it broke off. Who knows? And then it took 200,000 years or so for it to settle after that break, because it was probably awfully hot, anything that caused that big a break. And when it started re-solidifying, the hot rock in the middle was still doing volcanic activity for about another 700,000 years. And that's what formed the Maria. And then finally everything settled down and nothing much has happened since. Anyway, that's the one timeline. We'll see another one. In fact, here it is right here. The history of the moon. And by the way, they mentioned the Apollo missions. They are listed on my page 423. And you'll see here that the early ones, Apollo 1, 7, 8, some of those, they, Apollo 1, in fact, I had forgotten this. I was thinking it was earlier. Apollo 1 was a disaster. The crew died in their spacecraft during a test 3 weeks before they would have gone into space. They were in there doing a test and something exploded. Something went terribly wrong. And that's why it was 6 more before they ever put people back in them again. They tested trying to figure out what they were. Those 3 astronauts that died in Apollo 1, does anyone happen to know their names? I bet you some of you do. Are any of you at all familiar with Huntsville? Okay? Can you think of one of the high schools in Huntsville? Grissom High School. My wife graduated from there. Named after Gus Grissom. He was the commander of that flight. That's why they named it. You know, Huntsville is Space City, right?
Yeah, I grew up in that area.
You did grow up in the area. Well, one of the I think it was the next high school built after that exploded was Grissom High School. The next junior high built, and I may have these two crossed up, was Ed White, I believe. And the next grammar school that was built was the Roger Chaffee Grammar School. So they have a Grissom High School, I think it's Ed White Junior High or Middle School, and Chaffee Elementary School, named after those 3 astronauts that died in Apollo 1. And then you go on down the list, and the one that's the most famous, perhaps, was then Apollo 11. That was when they actually first landed on the moon. Neil Armstrong, Buzz Aldrin, and Mike Collins. Mike Collins didn't actually land. He was commander of he stayed out orbiting, and Aldrin and Grissom.
That why everybody just forgets him?
What's that?
That why everybody just forgets him?
That everybody does what?
Forgets him.
They did what?
Forgets him.
Forget him, absolutely. No one remembers his name. He was out driving the bus for him, and somebody had to stay. Okay. All right. So those are the ones. Then Apollo 13 was the one that first abort in deep space, and they had to come back in the lunar module. Okay. Wow. Talk about careful flying. They weren't designed to do that, but they did it. I mean, they designed so they could. They probably thought they'd never have to. So anyway, so let's now look at the history of the moon. This is probably a pretty good place to go on and make our move, right? So take a little bit of a break if you need it, and we'll move to, let me make sure the room's open. There was a class in there, but I think we're out now. Yeah, 261's open. You can move that way. If you need a little break, what you do, brain ankle or knee surgery? Okay. Arthroscopic or better kind of?
Yes.
Yeah.
Still painful, but not as
Yeah. Were you having pain before?
bad.
Yeah. Is this pain less than that pain?
Oh, I got pain.
Is this pain less than that pain? Or about the same?
Yes, my knee is like back down to a normal size now.
Right.
My right knee is like 2 inches bigger than my left.
Wow.
Yeah.
I'm glad it's better.
They said it was abnormal. I had a lot of blood on my knees.
Uh-huh.
Not normal.
No. Okay.
But they got it all out.
we've covered so far? Okay, do y'all need the backlight on? Can you still see that okay? Okay. All right. It's really hard to stand in front of the computer in this one because it's here and that's there. Okay. So, stage 1 of the moon. We think, that room over there, they have a door stop. They don't want me to close the door. This one, I'm afraid I'll be involved in too many people. They think it's formed from material ejected from a collision with some incredibly large object colliding with the Earth. And they don't put a particular date on this, or at least not on the slide. Is it in the Earth, in the book? Okay? Now, by the way, and they didn't put this on the slide, the moon rocks brought back from the Earth, the results of lunar seismographs, those are things that measure earthquakes, or moonquakes they would be, and other data gathered through the Apollo missions have increased our knowledge about the moon, leading to this new understanding of how it was formed. This model pictures the moon developing through 4 distinct stages, and here's what we're talking about. The origin stage. And the sad news to me is they do not say when they think this happened. Just say that it formed from material ejected from a collision of some large object with the Earth. Now, silly me, but the guy at Stanford, and he may talk about it this time, he may not. Just about every time we go, he has a different presentation. Not that he ever contradicts himself, he just talks about different things. But one of the last times we went, he said, the theory is that's why Venus turns backward. They had a major collision with something, and it knocked their orbit spin to go in the opposite direction. Never has recovered. So, I don't know what would have happened to Uranus. Maybe something like that did too. I don't know. So anyway, that's the origin stage. And unfortunately, they don't put years on it. Stage 2, okay, so picture this. Some enormous collision with the Earth, okay? Some enormous object, large object, collided with the Earth, broke off part of it, and that became the moon out there. Now, that major of a collision would have had to have produced an awful lot of heat. And in producing the heat, that's both on the Earth and on the moon, that would have then been molten surface on both of them. And this is why I think this was back in what they call the protoplanet stage. I think this was early on in Earth formation when we were still mostly melted. Anyway, we're just coming out of being part of the sun, you know, or its explosions that produce the sun. And that would have made sense then, that it broke apart. But we probably were beginning to solidify a little bit, but it was. So the moon, big enough, then it formed an almost spherical body, and we formed an almost spherical body. Okay? Now, stage 2, the molten surface stage. That would have produced enough heat that probably that whole chunk that blew off was melted. I mean, it was hot, okay? And that molten surface was about 100 kilometers deep. They think this lasted for about 200 million years after the collision, okay? The heating, they also think that continued heating from solar system debris impacts, okay? Remember, I think this was early in the Earth's formation, so therefore there was a lot of space junk flying around there that are getting hit. So it kept it hot for about 200 million years. Now that sounds like an awfully long time, but we're talking about an awful lot of heat too. A lot of stuff going on, okay? Stage 3, the molten interior stage. The accumulated heat from radioactive decay. So this again leads me to think this was back when the sun was still forming the solar system. There was a lot of radioactive material flying around out there from the explosions and stuff. So the accumulated heat from that radioactive decay, I knew Carrie was coming back. All right. Fine, there you are. All right, good deal. Okay. Looking at the history of the moon, the 4 stages, we're on stage 3. Accumulated heat from the radioactive decay, and this is where they got some things wrong. If you look in your book, I could not believe that the numbers would be similar, but the order of magnitude was so different. This is not 3.18 million years to 3.1 million years. This is 3.8 billion. Do it every time. Okay, 3.8 billion years. Whoops, let me get my pen back to, can I get it? Yes, okay. This is billion years ago, and this is billion years ago, and this is billion years ago. So, all right. Molten interior stage. The interior is molten. Finally, after 200 million years of molten exterior, slowly that's cooled, so now you got the crust. Okay? 200 million years to 3.8 billion, that adds up to 4 billion. When were the highlands formed? 4 billion years ago, the light-colored highlands. So that makes sense. Those are billions, they're not millions. So the surface has begun to cool and crystallize and harden, but the interior is still molten. Molten interior, very likely to have a lot of seismic activity, volcanic activity. This is when the Maria were formed. Go back to the previous slide, 3.1 to 3.8 billion years. There it is. This is making sense. Sort of, isn't it? Okay? And so that was all going on there. The interior is molten, melted. That's ripe for volcanic activity. And that was when the Maria was formed from the previous slide. And then, starting about 3.1 billion years ago till the present, the moon's been basically cold and quiet. Not much happening. Not much volcanic activity. I think they have detected a few moonquakes, you know, sort of like earthquakes, which means you still got some seismic activity going on, but it's minor. No big eruptions or anything. So basically, we're in the present, and we've been there for about 3.1 billion years for the moon. Been pretty quiet ever since. Now, what they don't tell us is this was 700,000 years in this stage, 700 million years in this stage, 200 million years in that stage. How long ago was that? Something before 4 billion years ago. Okay? So, I just don't know. We feel like the sun is about how old? We think it has a lifespan of about 10 billion years. We think it's been through about 5 billion of those. Right? Is that what you got? Okay. About 5 billion years. So this would have been early in the solar system process. Looks like that's when the moon. So that early collision probably came when we were just in our formation stage. That would have made it easier for some space junk to be flying through there and clam into us and broke it. I'm pretty sure we still didn't have any life by then. Probably not even any algae or molds or things like this. Maybe a little bit, I don't know. Maybe that collision planted stuff here. I don't know. It's hard to say, but we were not the planet we are now, and certainly the moon was not. So that kind of makes sense. Okay? Any questions on that? All right, now let's look. That's the history of the moon. Is this the last section here, or is this the last section? Last section. The Earth-Moon system. Okay? Section 16.5. Now, as I've said several times, and saying it a slightly different way, the ratio of the moon's mass to Earth mass is by far the highest mass ratio of any moon to planet in the solar system. The largest moon, I think, in the solar system is Titan, around Saturn, but Saturn is so incredibly huge, and Titan's just, not that much bigger than our moon. Yeah, no comparison. And then Jupiter has 4 moons that are bigger than the Earth's moon, and those are the ratio is much less than what our ratio is. Ours is by far the largest. Diameter is about a quarter of that of the Earth. So if this is the Earth here, the moon would be maybe about a ball like that. Maybe a softball. Does that look about right? Diameter about a quarter of that. Okay? And that's pretty big. The mass is about 1/81st that of the Earth. Now wait a minute. Why would the mass be so much less than the diameter? Well, most of the mass, the densest part of the mass is in the interior, and our Earth is much denser interior than the moon would be. So yeah, it's going to be. And then too, the mass, if you quarter the diameter, you're already down to 1/16 of the mass anyway, because pi r squared, those kinds of things. In fact, cubed, 1/64th, okay, because the volume is 4/3 pi r cubed. So you would be down to 1/64th just based on the diameter. Then when you include it with that, the less pressure that's inside, yeah, it wouldn't be nearly as dense. Large enough to affect the Earth's orbit. So this softball that's going around this beach ball here, okay, when it goes around, it's actually making the Earth change slightly, not much. The Earth is doing sort of like this when it's doing like this, but it still alters our path. I think they have a slide that shows that. Yeah. If it had negligible mass, it wouldn't matter where it was. We'd be moving in a straight line. It'd just be going around us. Yeah.
Doesn't the moon control the tides?
What's that?
Doesn't the moon control the tides?
Yes, we're going to get to that later. You're absolutely right, and this is why it does. You're absolutely right. And it's not just the moon, the sun is involved with it too. But the moon's a major feature. You're absolutely right. If the moon had negligible mass, it wouldn't matter. It'd be going around, we'd be going almost a straight line. But because the moon's mass is bigger than negligible, that means when the moon's over here, it pushes us that way. When the moon's here, it pushes us that way. When the moon's here, it pushes us that way. Our center of mass stays the same. That doesn't look like it is, but the x's should be in a line here, just like these are. But the Earth wobbles, not wobbles, jiggles in the path because of the moon going around us. Okay? This one looks like it out of the line, But our center of mass is still within the Earth's radius, but it's not at our center. It's slightly off. Okay? The Earth and Moon rotate about a common center of mass. That's what this is trying to show. It's not a great picture, but it's pretty good. Okay. I keep wanting to press the button here, so I have to walk in front. Okay. Now, the moon does have phases. This is the thing we probably recognize and know the best about the moon, these phases of the moon. It results from the changing relative position of the Earth, Sun, and Moon. Okay. Now, I think, Shelby, you're going to have to be the sun for us today. You're pretty bright, right? Okay. Okay. Now, no matter what thing we are, Shelby's the sun, here's the moon. How much of the moon do you see?
I see just that one half.
Yeah, you always see half of the moon. But how much of the moon do we see? That same half. Because all of that half that you are shining on is, people are seeing. That's what we call a full moon. Now, when the moon's over here, you still see all of it, right? But how much does the Earth see?
Just part of it.
Just exactly half of it. The front half is light, the second back half. If the moon's over here, you still see half of it, but we don't see any of it. We see the dark side of the moon. Okay? Over here, you're back to half the moon again. That's why the phases occur. Now, when it's just slightly off here, we begin to see a little crescent. And that crescent grows until it's half moon, keeps growing until it's a full moon. And then starts waning, getting smaller, until it's half moon again, and waning back to a crescent until it's a new moon again. New moon is when we can't see any of it. Okay. Now, what is this doing? Well, it quit doing it. Okay, good. You must have been thinking real hard. You disturbed the machine. Okay. You sent some waves up there. All right. Now, to do according to this, they started with the new moon here. Earth being here, we don't see any of the lighted part of the moon. Okay? And then this is what they call the first quarter. This is called the full moon, last quarter. This is half moon, that's a half moon. It's just, this is the first half of the moon. This is the last quarter of the moon. Okay. Now, here's the interesting thing. The sun, if you were living on the sun, you'd be burnt to a crisp, but if you were living there, somehow, you would see all the sides of the moon. You see the sides toward the earth when we were back here, and she did come back. Brandon was saying you were gone for good. I'm standing. Oh, never mind that. Okay. All right.
That kind of line.
All right. I just made that up. Okay. But the same side always points to the earth, which again leads to the idea that it may have broken off the earth. That would kind of make sense. And that the heavy sides out there and the thinner sides in here, all is making sense. Okay? Why would it have the same rotation as it would revolution unless there was some sort of explanation like that? Interesting. Okay. Now, this shows what we were just talking about. In fact, the next lab, the lab on this chapter, we're going to do something that looks very, very, very similar to that. Okay? We still got a decision to make. I'll give you another option a little bit later. Okay. And here's what they were. This is where it's starting with the new moon. The sun, remember, was over there. That's Shelby right here. And here was the earth, the new moon there. Always half of the moon is illuminated by the sun. Just like half of the earth is illuminated by the sun. Just happens we were on the side that's illuminated now. Over in China, they're in the middle of the night, you know, or somewhere over there they are, okay? And as it goes around, again, counterclockwise, okay? When it gets here, we see half of the moon illuminated. Here we see nothing illuminated. That's the new moon. Here we see half the moon illuminated. That's the first quarter, also called a half moon. Over here we see the full moon illuminated. All the side that's illuminated we can see from us. And over here we see half moon. That's called the last quarter, third quarter. You would think the last quarter would be the fourth quarter, but it's not. That's the fourth. Okay, never mind. And the fifth quarter is a bar. Never mind that. Okay. So the last quarter, or the third quarter, that would be the better one. But first and last, first and third, whatever you want to call it. Okay. Here's the other interesting thing about this, and this will impact you on your next lab. Okay? Notice where the new moon is. New moon is always between us and the sun. So as we're spinning, basically the new moon's rising at the same time the sun's rising, because they're in line with each other. So there is. Now we won't always see it because the sun is so bright and there's nothing of the moon showing, but every now and then you may actually see in the middle of the day a moon out there, but it's none of it's bright. You just see the shape of the moon. That's because it's very close to a new moon. Over here, the moon rises at around 6 in the morning and sets around 6 in the evening, because that's when the sun does. It's on the same side of the sun. The writing is because of the spin of the earth, not because they're doing anything. Over here, guess when the moon rises? It's exactly opposite of the sun. So the moon would be rising when the sun's setting. So let's say around 6 p.m. So and it would be setting around 6 a.m. So on the full moon, you're going to see it almost all night long. At least 12 hours. Okay? Then think about these. Okay? If this is when the sun's coming up, and this is when the sun's going down, this is probably rising around 12 noon and setting around midnight. So you're not going to see the half moon, but about half the night. Huh. Same thing here, only this will be rising around midnight and setting around 6 a.m. Okay? And in between, you'll see other portions of it. So part of the next lab, you've got to go out and make observations of the moon. We'll get to that in a little bit later. And you'll have to pick about a 2-week period, because that's about the only time you're going to, you'll be able to see the moon about 2 weeks, and then the next 2 weeks you won't see it at that time of day. At a different time of day, you'll see it, then, but you'll be picking one time of day and observing it at the same time. You're only going to see it about 2 weeks, consistent, and then for 2 weeks you won't see it at that time of day. That's going to be part of the next lab. Okay, so hang on to that concept. You're going to see it again when we do the next lab. That's why I wish I'd have gotten here in time today, and we would have been basically through with this and ready for the lab. Now, when you do see that crescent moon, remember there's 2 times you'll see it: when it's just past new moon or just before a new moon. How can you tell which is which? Well, the part that's lit is always the part toward the sun. Okay, so most of it is the back side you can't see, but here's the thickest part that's pointing toward the sun. So if it's in the morning, if that's pointing, if that crescent is so that the west, that's west. Oh wait, in the morning that would be east, in the evening that would be west. Okay, so just depends on which time of day you see it, but that's pointing toward the sun. The sun's rising from the east and setting in the west. That's always going to be pointing toward the sun. Always. Take the tips of that crescent, draw your line there perpendicular to that through the thickest part. That's pointing toward the sun. Has to be. All right. Now, before we do any more, there's a little blurb here. I like their little blurbs, don't you? It's moon mistakes and misunderstandings. Moon mistakes. Here's why. It's a common misunderstanding that it's the Earth's shadow that creates the moon phases. No. It's the portion of the moon being lit by the sun when you got most of the moon facing the sun and only a little bit facing the Earth. That's when we have done. That's not a measure of our shadow. That's a measure of the moon's curvature. That's all you're seeing. Number 2, here's one that's pretty interesting. The phrase "a blue moon." Does anyone know what that means?
Something on the moon looks kind of bluish color.
Okay, good try, but not quite. Here's what it means. Not a reference to the color of the moon. Instead, it is a reference to, and this actually only happens occasionally, it's when you get a full moon twice in 1 month. Remember the synodic moon that we had in an earlier slide is about 29 and a half days, right? Okay. Now, most months have 30 or 31 days. Okay. So, February will never have 2 full moons in it because it's only 28 days. And even on a leap year, it's 29. You'll never have 2 full moons in a February. Well, the other months, rarely, but occasionally you will have. And when that happens, 2 full moons in 1 month, that's, I think it's the second one, it's called the blue moon. So once in a blue moon is not very frequent. To me, that should have meant 2 new moons in 1 month. Those are blue moons to me, but no, it's not. It's the new moon, full moons. 2 full moons in 1 month. That would be a new blue moon, not new moon, blue. And the third, a popular myth has more accidents happening during the full moon phase. However, studies have found no statistical significant relationship between the accident rate and the moon phase. This myth probably is a result of people remembering the full moon phase, but not the other phases when they saw an accident. Okay, maybe so. But we one time had a neighbor. This isn't science here, it just happened. We had a neighbor who was wacko. He just was fly off the handle. He put acid on other neighbors' cars. He threw rocks through 2 of our picture windows. He would just help. And we started noticing this seemed to happen really close to full moons.
My aunt worked in the psych ward at a hospital, and
Right.
she said they would get extra crazy on full moon.
On the full moon. And so there is something that happens there. Maybe not accidents, but I would have thought accidents followed that same pattern. But really, there's something going on the that really isn't, because we noticed that Bill Brothers just went nuts. He called the police one time on another neighbor, claiming that there are dogs attacked either him or somebody in the neighborhood. Well, that neighbor had left really early that morning before and hadn't gotten home yet when he called the police. Well, her dogs were up on the second floor balcony. She was in an upstairs apartment. So we called them the vine climbing dogs. You know, they climb down, attack them, and then climb back up. Because all the neighbors said, nope, those dogs have been up there all day. No one's been there to let them out. Couldn't happen. You know. But anyway, not physical science. Maybe mental science, I don't know, but not physical. All right, next thing we're going to talk about, eclipses. We've been talking about ecliptics, which have to do with eclipses, but now we're going to talk about the actual eclipses of the sun and moon. If it's an eclipse of the sun, what do we call that eclipse? A solar eclipse, lunar eclipse. And you talk about the psych ward. Where do you think the name lunatic came from? Lunar. Okay, yeah. They felt like it had something to do with the moon. Okay. So the moon's orbit is inclined about 5 degrees from that of the Earth. So notice when I was talking about this, I always had the moon up here. I could have had it down here somewhere. It's not quite going around the Earth. It's not certainly not going around the ecliptic of the sun. It's off by about 5 degrees. So therefore, most of the time, we're not in line with each other at all. Okay? But when you have that proper alignment, all that time when that 5-degree ecliptic happens to become in between us and the sun, then we can have an eclipse. If the moon goes there, the moon is eclipsing the sun. We have a solar eclipse. If the moon's back here, lined up perfectly, then we have a lunar eclipse. Which of those you think is more frequent? The lunar eclipse, much more frequent. Why? Okay, the moon is closer to us, but the other thing is we have a lot bigger shadow than the moon does. So when the moon's here, it's the shadow that's hitting the Earth. That's going to be a pretty small shadow. When the moon's back here, the Earth has a huge shadow. Lots of people will see a lunar eclipse. There's a lot more shadow for it to go through. So that's the other reason. The other thing is the closeness you're right. Okay? Now, I don't think, yeah, this slide does okay with it. I wish they had it a little bit better. But remember the sun's over here. You can tell because of the shadow there. Here's the sun over here somewhere. Way over here. And way over here. And the moon is pretty small, and its shadow is a conical shadow because there's parts of the sun that shine on the moon, and the sun's so big that, you know, it doesn't form, it has a little bit of a shadow here, but the dark shadow, the deep shadow is here. Actually, 2 pieces of the shadow. They call the umbra and the penumbra. That's going to come up in fact, it's the next thing. Let's go on and hit that then. Okay. The conical shadows have two parts. They're only showing the umbra here. The inner cone, the complete shadow, complete dark. None of the sun's rays make it there. And most of the time, the moon's umbra doesn't even touch the earth. So that's why most of the time there is no solar eclipse. It's just out there in space somewhere. But when this moon happened to be here, now they don't have this right, but let's imagine things get twisted a little bit here. And this is where now the sun's down here. I don't know how it got down here, but it's down here so that the moon's umbra is going to hit the earth. Now they also have the dimensions a little off here. And when the moon's umbra does touch the earth, that's when there's a solar eclipse. A total solar eclipse. When the umbra hits this. But that's such a small umbra, and it gets smaller, and actually it's sort of a short umbra too. Remember, the Earth is in an elliptical orbit around the sun. Well, so is the moon in an elliptical orbit around the Earth. Okay? And remember, this is a 5 degree. Here's the plane of the Earth's orbit, and here's the plane of the moon's rotational orbit. That's off by 5 degrees. So most of the time, that's not going to touch at all. You won't have a lunar eclipse. But, okay, now let's get this right too. When are we going to have a lunar eclipse? Oh, I'm sorry. Solar eclipse. Is that going to be when the moon's over here when it's full? No, that's when we could have a lunar eclipse, not a solar eclipse. Solar eclipse is when the moon is a new moon. You can hardly see it. It gets in front of the sun, and that happens to happen when the Birmingham, Alabama is part of that umbra. It touches here. Okay. Now, that's pretty rare for it to occur, but it does occur. Okay. The umbra is that inner cone, complete shadow. The penumbra, they don't show it here, but that would be when rays from this part of the sun, or this part of the sun, do come, but this part of the sun does not. So you have a sort of a cone that goes the other way here, and that would be the penumbra, a partial shadow. Not a total shadow, a partial shadow. It's kind of like there. You see my finger shadow? That is all umbra pretty much, all completely dark. Can I get it? There. Now, the middle part of my finger, it's not my middle finger, the middle part of my finger is umbra, but you see that fuzziness around it? That's the penumbra. You see the gray areas around it. Penumbra. Very little penumbra there. I can't see any, but you saw it more there. Now, let's imagine that was far enough away to be the sun, and the moon was somewhere here, say, there'd be a lot of penumbra. Okay? Very little umbra. Okay? That's why this shadow, see, we're too close to the light there to have a really good umbra. Okay? So, keep that in mind. Now, what I wish that had shown on this slide too is the umbra for the Earth. The Earth is much bigger. It's going to have a much bigger umbra area. And the moon could easily cross into that. Pretty hard for the Earth this to hit the Earth. Sometimes it doesn't even reach it because, again, the moon has an elliptical orbit. When it's way out there in orbit and that's what's lined up, it doesn't even reach it. The umbra never touches the Earth. We'll talk about that in just a minute. Yeah, right there. Okay? Other times it will touch the Earth and make a little area. It's a very small area of the Earth. So, the solar eclipses are when the moon is in between the sun and the Earth. The tip of the umbra touches the Earth. That's going to be a total solar eclipse. When that happens to be at the place where the moon is farthest from the sun, and that doesn't even reach it, then we will have what they call an annular eclipse. When you have it, you'll still see the sun around the moon because the umbra doesn't quite reach us. We're all in that shadow a little bit. We're in the penumbra a little bit. But that's an annular eclipse. You'll see the moon inside and the sun around it. Don't look at the sun even then. I mean, you're tempted to. It's really pretty. Take a picture of it, but don't look at it yourself. Look at a reflection of it, or something like that.
Wear sunglasses.
Yeah, or wear very, very dark sunglasses. Yeah, you could do that. Okay. Now, better to get welding, the mask that welders use, that would be adequate. That would be better than even dark sunglasses. Okay. Lunar eclipses, that's when the Earth's umbra, which is much bigger, the moon crosses it. The moon being smaller, it's easy to get buried in that one. And that's when you have a total lunar eclipse. Total solar eclipses happen very rarely, only for small bands on the Earth's surface, and sometimes don't even happen completely when you have the annular eclipse. You'll have a partial solar eclipse when you're in the penumbra. The lunar eclipses, though, the moon gets completely engulfed with that. Okay. So let's talk a little bit about frequency here. Oh, no, here we go. Here's a better picture. Okay. Now, this again, the dimensions aren't right. The sun's much further away than this. That would be Venus right there. I mean, Venus would be right here, so this isn't dimensionally correct, but you get the idea of it here. The sun here, you see rays go from the sun and do like this. No rays of the sun reach into the umbra. In the penumbra, these rays are completely blacked out here, but some of the rays here go in this region. That's penumbra, and some go up here. The upper part gets hit by the sun. This part does not get hit. So this is the penumbra. So this will be total solar eclipse here, partial solar eclipse in those regions. And again, they got it greatly exaggerated because they have the sun way too close to, So, but that's why you have a partial solar eclipse for a narrow band, and a very narrow band you'll see the total solar eclipse. Now, when the moon's a little bit further out and this cone doesn't quite reach the surface of Earth, that would be your annular eclipse. You'll still see a little bit of the sun around the shadow of the moon. Okay. Now, are they going to show the table or not? No, they're not. Shame on them. Let me go over the table with you just briefly. And they still didn't show the Earth's umbra and penumbra, but you can imagine that from the others. Total eclipses in the U.S. from 2010, which is already way past, to 2025, which is still in the future. The next total solar eclipse, August the 21st of this year. Now this is in the U.S. Some other part of the globe could have it other times, but here, this we'll see. That's from Oregon to South Carolina. Okay? Oregon here, South Carolina here, we're not in that line. Looks like if you drove up to Tennessee or possibly Kentucky, somewhere around in there, probably Tennessee, you might be able to catch it. So watch out for that this August. Not going to happen frequently in your lifetime. So take advantage of it if you can make a trip up there. The next one, April the 8th, 2024. Goodness gracious. That's another 7 years away. I'll be 73 years old, okay? Oh, well, where is the sun? Yeah, never mind. We won't go there. Okay, now that path is from Texas to Maine. Yeah, it misses us again. Depends on what part of Texas, but I doubt if it's up. But it does look like if we went up into Tennessee, maybe around Memphis or so, we might catch that. So 7 years from now, y'all will still be alive and kicking, so take advantage of that one too. Total lunar eclipses, we've already had, and this This was in a 15-year period, 2 total solar eclipses in the U.S. period, continental U.S. anyway. Lunar eclipses in those same 15-year period, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now these are total lunar eclipses. You can have partials in there, but totals 9 in the U.S. Okay? And this will be most of the U.S., but not maybe all of them. We've already had the ones, 2 that were in 2014, 2 in 2015. That's old history. The next one coming up is next year, 1 year and a week or so from now, you'll have the next total lunar eclipse. This will be January 31st, 2018. Visible at moonset. Okay? Again, when do we see a lunar eclipse? The full moon. And the full moon is going to be happening when a moonset is going to be near sunrise. You might have to get up early that day. Okay? If you want to see a total lunar eclipse, visible at moonrise. And it says, that's all it says. At moon, I'm sorry. Visible at moonset, which will be near sunrise. Well, 31st of January, sun comes up pretty late anyway, so you might be able to see that. Okay? Get up a little early that day. The next year, almost a year away, January 21st, 2019, is visible, I guess, about all night long. Okay, so that will be a fun one. Hopefully I'll still be teaching then. May 26, 2021, I'll probably be retired by then, but that's going to be visible at moonset, which will be near sunrise. And then May 16th, almost a year apart, funny isn't it? Visible at moonrise, which is sunset in the western, and you can see it all night in the eastern. And then 2025, be pretty old by then. Visible everywhere. March 14th. Okay. So did want to hit those. All right. Any questions on eclipses as opposed to ellipses? Okay. So what Brandon? No, who was it? Yeah, you mentioned the tides. The tides. Okay. Not the crimson ones, but the other ones, okay? The tides are the result of different gravitational pulls on the front and back of the Earth, okay? Let's get our situation again. Shelby's our sun again, right? Now, when the moon's over here on the same side as the sun, guess what? Maximum gravitational pull this way. Anything along here is going to have a high tide. Yeah. And the Earth's spinning, so you get high tides all there. The surprising thing is you also get high tides here. Your low tides are here and here. The reason for this is that extra strong gravitational pull is pulling the waters that way, but it's also pulling the Earth that way, which leaves water back this way too. So you get high tides on both sides, low tides on this side. That's why you have 2 high tides a day and 2 low tides a day, most days. All right. Now, similarly, if the moon's back here and the Earth's here, now again, you get maximum high tides here, front and back, and low tides here on the sides. All right. Now, I've just given a couple of things, but not all of them. Result from different gravitational pulls on the front and back of the Earth. 3 factors. First is the Earth, Moon, Sun positions. Now, the spring tides have nothing to do with the spring of the year. That's not what it's talking about. They are when the 3 are aligned. That's when you have your maximum high tide. When you have Earth, Moon, Sun, Sun, Moon, Earth, or Sun, Earth, Moon. Those are going to be your spring tides, maximum, and those 3 are aligned. The neap tides are when the moon and the sun are at 90 degrees. So if the sun's there and the moon's over here, then you're going to have the weakest high tides and low tides as well, okay? That's the neap tides when they're at 90 degrees from each other. One's pulling one way, the other's pulling the other way. You still have high tides. Now, the elliptical orbit of the moon, I mentioned that. There's sometimes when the moon is closer to the Earth, sometimes when it's further away. The greatest pull is at the perigee, that's when it's closest, and the least when it's at the apogee, that's when it's furthest away. So that's the other thing. You may have a spring tide, but it's going to be a bigger spring tide when the moon is close than when the moon's further away. And there's about a 48,000 kilometer difference, which is about a 25,000 mile difference. So that's a pretty significant difference. Now, the third has nothing to do with the sun or the moon or the alignment. It has to do with the size, shape, and depth of the water basin. Now, where do we have the smallest difference in tides? Good old Gulf of Mexico. It's a big old bathtub down there, and its tidal basin is such that it's nice, regular shaped and everything. Very little difference in high and low tide. About 1/3 of a meter, that's about a foot. Okay? That's all, folks. You know, not very far. The maximum, though, 15 meters in the Bay of Fundy. I think that's in Nova Scotia. I can't remember. I think I've looked it up a few times. It seems like that's where it was. What's 15 meters? Well, I just told you that I'm about 2 meters. The ceiling is about 3 meters. That's a 5-story building. Low tide to high tide, 5 stories. How in the world do you plan your beach with that? Okay, if you got that much variation. Literally what people do with those kinds of tides, they have huge poles that have to be at least that 5-meter high, and they tie their boats up to them on rings that can go up and down. Otherwise, the boats would be swamped, or I don't know what they would do. I don't know. I think they do rings around the column. No, Bay of Fundy. I think in Nova Scotia. A narrow bay, and the land falling off at a certain thing. The size, shape, and depth of the water basin. Okay. Now, here's what we were talking about before. When you have, and by the way, remember, the moon's the predominant thing with the tides. The sun contributes a little bit. That's why you have your spring tides when the three line up. Either sun, moon, earth, or sun, earth, moon. That's your spring tides. Okay. But when it's over here, the moon wins. Here's the high tide on the side of the moon. It's just not as great as when the sun is there. Okay? The moon's over here. The gravitational pull of the moon attracts the water, which is more mobile than the earth is, so the water comes pulling this way. Okay? But it also pulls the earth a little bit that way. But that also leaves a little bit water behind this way. So you have your high tides here and here, your low tides there and there. Okay, the tidal bulge that's left behind as the earth is pulled away, and the tidal bulge created when the water is pulled from the earth. So the water is the thing that shifts. The earth moves a little bit, but not too much. Does that make sense? The moon is the predominant. When the sun is in a line, it contributes. When it's not in a line, it reduces a little bit, but it's still the moon. And that's all, folks. The slides, okay? There is one blurb here. People behind the science. Now, why they picked out this chapter to put Carl Edward Sagan there? He was a very good communicator of science, okay? He may have been a pretty good scientist. He must have been. But he was great at communicating science. But I don't know all that many discoveries he made himself, but he was just really excellent at communicating the meaning of science and stuff. My brother loved him. I think he's read every book he ever wrote. He watched them on, was it Nova? Was that PBS? Huh? Cosmos, maybe that was the name of it, that he was it on public television? Wherever it was. But you could write on him, but if you read this, you'll find several other things you could write on. But he did do some pretty major research on planetary surface, atmosphere of Venus, those kinds. So I don't mean to diminish him, but he was primarily a great communicator of science. Okay? So you can read other things. Guess what? This blurb is not a source. It's a source for an idea. You have to go to something outside the book to get your source for your paper, if you choose to write on him or something like that. And that ends the chapter. And again, I say it every chapter. I'll continue saying it every chapter. Nothing replaces reading the chapter. I actually had a student one time. He was one of my better students, I thought. He made pretty good grades. And I said this over and over. And then, I think it may have been a spring term. I think he came back from spring term, and the next test we took, I mean, that guy aced it. And then he commented to me when he did, he said, you're right, it really does help to read the chapter. I thought he had been a really good student before, but he was okay. But boy, when he read the chapter, he trounced all over that test. He said, it does make a difference. I thought, how many chapters have we been through, Okay, it wasn't a mini term, it was a full term. Okay. Read the chapter, but once you've read it, the summary does just that. It summarizes. Certainly can't get everything, but it hits the high points. And things to watch for, especially reading the chapter, boldface, italicized words, and then when you read the summary, especially italicized words. Then when you look, and this is as long a summary I think as I can remember so far, and then look at the key terms. That is a huge list. And I think you'll find most of those are the italicized or bold words in the text, So that gives them alphabetically, but you can find them by the page numbers that give that to you. And then applying the concept, to me this would be the best thing to study. About the average number, 47, that's pretty close to average, maybe a little more than average question, multiple choice questions. And as you saw in your test, you might have a few fill in the blank. The last test had 2, I think. And most tests won't have many more than that. Maybe 1 or 2 will have 3, I don't know. But most of them will be multiple choice tests, questions. They won't be these same questions, guaranteed, but they will be covering the same material. Maybe it'll be asked in a slightly different way. Then there's questions for thought, and I don't think I can recall a chapter with 31 questions for thought. So this has quite a few. I would definitely look at some of those just to make sure you understand it. You don't have to write them out or anything, but that would be a great thing to study. And then further analysis, 6, that's about average probably. And then the invitation to inquiry, I think, well, basically, this is going to be very close to what your lab is, the first part of your lab, okay? Actually, we'll talk about that. Then there's the parallel exercises. For those who have the big books, okay, I don't see any of you. If you do, you have the parallel A questions. They have the answers in the back. So I would work on some of those just to make sure you understood them. Any that are beyond what we've done, you can sort of skip. But the group B, they don't have answers in the back, and if you have the thin books, none of the answers in the back. All right. That gets us to 4 o'clock, a little after 4. And again, I think we have 2 choices now. The choice 1 would be, let's start chapter 17, and that would be fine. And then what we'll do next time, if we make that choice, continue 17, and then when we finish 17, or finish our first 2 hours, then we'll have the lab on chapter 16, and then we'll have the test. The lab, I'll allow you 2 hours. I don't think it'll take you 2 hours. And then I'll allow you 30 minutes for the test. I don't think it'll take you 30 minutes for chapter 16. Or the other option would be we'll have 1 hour of the lab for chapter 16 now, and let everybody else listen to it on Screencast-O-Matic on YouTube. And then next time we'll have 2.5 hours of class, an hour of lab, probably three hours of class, 2 hours of lab, and then 30 minutes. 1 hour of lab and 30 minutes of test. So we could do it either way. If you wanted to start the lab now, we could, or if you want to just wait and do the whole lab next time, we could do that too. Y'all have a preference? You want to do the first part of the lab now?
Yeah, that sounds like a better idea.
What's that?
Sounds like a better idea.
Okay. I think so too, because otherwise you have to listen to me yak. I have to listen to me yak in the lab too, but maybe it's a little different. Okay. So I'll pass out the lab, or I may just pass out. Okay, this one's on the phases of the moon. Now, do you have someone helping you now? You can. So you want to give you bud? Okay, one back to the angle. You get one. Okay. Oh, I don't think I said this at the beginning because we were so rushed for time. I did want, yeah, I think I did say this. I did. I told you about that on Thursday. My office hours are reduced to 30 minutes because I'll be doing the second tree class that day. Okay. All right. The first part of this lab, I think what I'm going to do, since I don't, well, I will need that a little bit, but since it's dark, I'll sit here. Okay. Phases of the moon. We just talked about it in class. Okay. I want to get here so it'll pick up better on the sound. Okay. And some of the things we were talking about: moonstruck, lunatic. Oh, are those similar? Never mind. The moonshine. From the hills of Appalachia, that has a special meaning. But anyway, a lot of interesting stuff there you can read. And here's what we're going to do for lab. Now, it's the first part of what's listed in the lab, and that's why I say it's the first part of the lab. But it's the last that you're going to do. It's the first part of the lab physically here. What you'll do is make about 6 observations of the moon in a 2-week period. And here's what I say shoot for. Shoot for observing the moon every other day. Now, if you did every other day for 2 weeks, you're going to get 7 observations. Okay? So if you shoot for 2 and say it's raining one night or so cloudy you can't see anything, then you'll miss a night. Do it the next night. Try to get 6 observations in a 2-week period. When does the 2 weeks begin? Okay? What I want you to do is the first thing you do is pick the time when you would like to make your observations. And basically this is a time that you need to have free. You're not going to do it every night, but you're going to need it free every night at the same time that you'll be able to go out and make your observation. That could be, like I put the dog out between 10 and 10:15 just about every night. If I were doing this, that's when I would choose, because I do that every night. Okay? Now, others of you might not be late night people. Who was it? I was talking with sometime recently. Oh yeah, a biology teacher. And she said, well, I go to bed at 9 o'clock. Yeah. She was talking about students emailing her at 10, 11, or 12 o'clock at night. She said, I'm asleep at 9 o'clock every night. So I thought, okay, she probably wouldn't be able to do this as a night one. She might need to do a morning one. If you're an early bird, then you choose the time when the moon's up. So I can't tell you when you need to do this. You need to know your own schedule and start observing the moon, or trying to observe the moon at that time that you're going to do it, and start this anytime from now on. Pick the time you can do it, Pick a place you can do it, okay? Now here's what, I had a guy who was the work-study person who helped the night coordinator here. He was in my class one time. So what he did, he worked till, I don't know, 10 o'clock or 9:30 or whatever time he did. He knew that right after that, he got off work, he went out into the parking lot, and that's where he did his observation. He knew that he'd be in that same place every night. Now, on weekends, when it was every other day fell on a weekend, I don't think he lived too far away, so he probably drove to campus and went there that night too. So, or he skipped the night there. I don't know what he did, but he did a pretty reasonable. Find your place. Now, what needs to be characteristic of your place? It's better for it to be an open area. You don't want it to be in the middle of woods, okay? You're not going to see the moon very well in the middle of the woods. Even in the wintertime when there aren't that many leaves on the tree, it's still not easy to do. So if I were doing it, my backyard is not particularly free of trees, but I can find the spot in the middle of it where it's the most free. That's where I would do it. If you have a parking lot nearby, a shopping center, a golf course, a football field, or a baseball field, you know, some sort of playing field, somewhere close by that's going to be safe, and you can go, and you know you can go and get to the same spot for 6 nights. You know, pick that spot and pick your time. So those are all compatible. The first 2 things to do, pick your spot, time, pick your spot. Okay? Now, what you'll do, you'll pay attention to 2 different, distinctly different things. If you flip over to page 380, second page, Part A, the observations. Okay? I've already hit on subtopic A. Okay? Choose a location for your observation. Find a place you know you can be, that same place, for a 2-week period, 6 times in that 2-week period, every other day approximately. Okay? Pick a place. Pick your time. Okay? Those go together. I mean, if it's a parking lot, but it's a mile from your house, I'm not suggesting you do that, but if that's what you chose, you'd probably rather do that at night than you would in the morning. That means getting up an hour early, or a mile, you know, so you could drive out there a mile, yeah. You choose. You fix them together. It is critical, notice under timing, it is critical that you make all your observations at the same time of night to within 15 minutes. So when I said I put the dog out about 10 to 10:15 every night, I would say I would pick probably 10:05, 10:10, or 10:15. I know I don't get her out there right at 10, so that would be too early. So I pick that, and then I know I could get within that 15 minutes. Okay? So pick your time, and you have a little bit of wiggle room, but not a lot, within 15 minutes. Because the weather may hamper your observations over the course of the observing period, you do not want to let many clear nights go by. If you have several days in a row of rain and then have 2 days in a row of clear, take those 2 days, even though it's not a day apart. You know, I said every other day, do 2 in a row. Okay? Do whatever it takes to get your 6 observations in a 2-week period. Okay? Try to do it every other day, at least to begin with. If it looks like you're not going to do it, go to every day. Okay. So what you need to do is pick your place and pick your time. Go out and start looking for the moon. Now, if you can see the moon already, you may already be in the middle of your 2-week period, or maybe at the end of your 2-week period. So you might want to wait until the next one comes around, okay? But if you can go out now at the time and can't see the moon then, start going out every night just to see if you can see the moon. And the first night you can, have that be your first night, okay? So before you see that moon the first night, here's what you need to do, okay? Like it said, choose a point for your observation. Go find that place and know that you can hit that same place every night. So if it was my backyard, I might actually put a stick in it, because I know I'll not mess with the stick. Of course, my dog may kind of think, oh, he wants to play with the stick, and carry it off. But I'll know right about, I have a small backyard. I can find it. Pretty much the spot. Okay? If it's, say, a parking lot, maybe take a can of paint and put a little circle on it or something like that. You know, don't deface it, but just something you can find. Okay? A little piece of red plastic or something like that, drive a nail in it. Or something. I mean, you know, do something that you hope no one's going to move that. Or after a while, you'll know exactly where that parking place was. You know, that's my parking place, you know. Okay. And pick it so you can do the time there too. Now, before you see the moon that first night, at your place, at your time, well, the time doesn't matter so much, but at your place, look around. So if I were looking around, I'd say, that Econo City ends. Okay, that's going to be one of my landmarks. Okay, I'll turn over here. Oh, Bessemer City School, the flagpole there, that's going to be my landmark. Go over here. It might be a tall tree. That's going to be a landmark. So find you a number of landmarks around that you know. When you're on your spot, I can see that, I can see this, I can see that. Find those landmarks on the horizon, all the way around. This is before you even are looking at the moon. These are night before the moons come up, you know, before you're out there. And the time doesn't matter as much, forget those. Okay. Now, once the moon's up that first night, then pick, wherever the moon is, pick the landmark it's closest to. Okay? And then do a little measurement. You might want to take a ruler out there with you. I would say a yardstick. And hold that yardstick up and do it from the horizon to the moon. And so read how many inches. Put the 0 on the bottom and the thing. 22 inches above the horizon. And hold it sideways 4 inches to the right of Bessemer City School flagpole, or whatever it is, whatever your landmark is. Identify where it is. Right or left, up and down. That's the thing you want. So that's your first thing. Where is the moon relative to your landmarks from your spot? Okay? That's your first observation. Second observation, where is the moon relative to some distinctly different looking set of stars? My favorite constellation is Orion. I don't know if y'all know what Orion looks like. I love Orion. It's so easy to pick out. If that moon's anywhere close to Orion, I'm going to have my yardstick. It's 14 inches to the right of Orion's belt or sword or something, and 3 inches above his shoulder. I'm going to use Orion because I know I can always pick out Orion. If it's nowhere close to Orion, Big Dipper. Okay? Right, left, up, down from the Big Dipper. Okay? If it's just this perfect little triangle of stars, I don't know what to call it. If you can find that triangle of stars every night, the moon's close to that first night, measure it from that, and then from now on, measure it from that same triangle of stars. Or anything. You pick out the stars near the moon that you can always pick out those stars and measure the moon from there. So, okay. Okay. The rest of it will be on YouTube. Okay. So pick the landmarks on the horizon before you ever see the moon. The first time you see the moon, measure it relative to those landmarks, but also pick out some group of stars that you know you can go back and find and measure the moon from that group of stars. And then every subsequent measure, you measure from that same group of stars and from that same landmark. Okay? The moon's going to move on you, and it'll move significantly. So you might have to take your yardstick and estimate more than 36 inches, you know, possibly. But get where it's moving, right or left, up or down, you know, from that group of stars. The stars aren't going to move much. The moon will. And it will move relative to your landmark here. So you could, if you have several landmarks and you know how far apart they are, you could go to a different landmark if you want to, but you have to know how far they are apart from your other landmark. Does that make sense? Okay. So you record those observations. You can make sketches they suggest you do. I don't care if you make a sketch or not, whatever you can remember. Okay? Take good notes. Okay? Now, I said, yes?
Why do you want me to do this?
Okay. Yeah, it's going to be really tough on you. That's why I was wondering. I don't guess you have anyone near that would be interested in doing this, do you?
Not anyone that's gonna be there at like moonrise.
Moon, yeah, or yeah. And you're probably not out a lot at night anyway, are you?
Well, I can see the moon very clearly from where my apartment is.
Yeah,
Problem is the recording.
yeah,
That's what's gonna be the issue.
yeah, that could be tough. I'll give you a pass on this part, but observe the moon, and if you make any observations, write them down.
Okay.
Okay, I'll give you credit for whatever observations you can do.
Okay.
Okay. So, those are the first two things. Now, if you don't want to take a yardstick there, to me that would be the easiest thing. Now, always hold the yardstick at arm's length. You know, don't be here one night and there one night. That's not going. Hold it the same way every night. Okay. If you don't want to use a hard yardstick, if you want to measure in degrees, they give some of these. I don't think it's worth it. That would be about 22 degrees, your outstretched hand. Your fist is about 8 degrees across. The width of your three middle fingers, that is going to be, whichever way you do it, about 5 degrees, and your index finger at arm's length is about 2 degrees. So if you want to use that, you can. I forget, I'd have to carry the piece of paper with me to remember those, whatever. You can do that. It says alternately you can carry a ruler. I think that would be the best, okay? But that's up to you. You can use whatever you want to help remember that. Okay, so those are two things. Moon relative to your landmarks on your horizon. Moon relative to some group of stars you can pick out every night. The third thing you record every time you see the moon is its phase, okay? And at the end of your observations, you've been keeping these observations, a little journal, a notebook, pieces of paper, whatever. Maybe, let's see, there's not a lot of room to write on here, but if you can find enough room, you could do it here. But at the end of those 2 weeks, from the time you first start observing the moon till the last, how would you describe, this is answer 381, on page 381, one at the bottom of the page. You can do as much of this as you can. How would you describe the night-to-night path of the moon with respect to the landmarks around your observing site? So is it going left to right, getting higher in the sky, lower in the sky, relative to that landmark? Okay? Now, if you can do it, if you're good at directions, you can actually call this east and west, north, south, and higher or lower. You can do it that way. Left to right is fine with me, okay? Number two, in which direction does the moon move with respect to the background stars from night to night? It moves away from them, or above them, or below them, or to the right or left of them, and it seems to be increasing every night. Or moving to the right and going down, moving to the left and going up. Or, if you're good at directions, moving to the west or east and getting higher or lower in the sky. Whatever. Give your best description of how it's moving relative to landmarks on the earth, relative to stars in the sky. That's the first. Those are those two observations. Then your third one on the phases of the moon. This is the fraction illuminated. This is on the top of page 382. Okay. The first night you see the moon at your location, at your time, that's night 0. And that moon will be either a new moon, a crescent moon, which will be between 0 and 1/4. The fraction of a moon illuminated, okay, this is not very fair. 1/4 of a moon, you estimate that. So is it less than 1/4, between 1/4 and 1/2 or 1/2, between 1/2 and 3/4 or 3/4, or between 3/4 and a full moon? 1 is a full moon. So wherever that first night, you put it on the 0, and then if you do every other night, the next night will be night 2. If that second night away is cloudy or rainy or something, you can't do it, or you're out of town, then you go to the third night, and then you record that. And you'll see some sort of a pattern. It's either going to be rising, falling, falling, rising. It's going to be changing night to night. Fill that in. You can do that, right? So answer the two questions. This is at the end. And I would mark, when I go out there and do it, I would mark the phase on this every night. The other stuff write in your book or notebook or piece of paper or whatever. But this one, I would carry this with me every night. Okay. Now, that's the first part of the lab, but that's the last part you'll do. The last part of the lab, part B, we're going to do starting today. We may not finish it. We'll finish it on Thursday, okay? So that's what we're going to do now. Lunar phase nomenclature. So all of you should get this part, okay? Do the best you can on the first three questions, okay? But don't say, oh, I never got to observe the moon, and so don't turn it in. If you're here or if you're listening on YouTube, you should be able to do the second part, which is the most points anyway, so at least turn in this part. Okay, the explanation of the phases is quite simple. The moon's a sphere, but what we see is basically a circle, okay? And at all times, the side that faces the sun is illuminated, the side that faces away from the sun is dark. From previous drawings, you see that the phase of the moon that we see from the Earth as the moon revolves around us depends only on the relative orientation of the sun, the moon, and the Earth. That's all. So here are the nomenclature terms. When the moon is almost exactly between the Earth and the sun. Now, it doesn't mean an eclipse. It means it's on that side of the sun, above, below, wherever. Then all you see is the dark side. You don't see any part lit. You may not even see it because all you see is the dark side. That's a new moon. Okay? Okay, if you can see the sort of a shape of a moon, you know it's there, but you don't see any of it lit, that's probably a new moon. Now, a few days either after that or before that, you might see just a little sliver of the moon lit. That's called a crescent moon. And looking at the table there, anything less than half a moon is a crescent moon. Okay? As the month wears on, the crescent gets bigger and bigger until one night you look out there and you see almost exactly half of a moon. That's called a half moon. Usually called a first quarter or a third quarter moon, sometimes called the last quarter moon, but it's a half moon. So that's your nomenclature. Also called the first quarter moon. But then when more than the half of the moon is visible, you got the half moon plus some, a bulge on the other side. That's now called a gibbous moon. Now I use the term crescent. I seldom, if ever, except for this, use the term gibbous. I don't even know what it is. Gibbous. That's a gibbous. More than half a moon is lit. Okay? When the moon is on the opposite side of the Earth from the sun, but not in an Earth shadow in an eclipse, then the entire face of the moon is illuminated, and we call that a full moon. Exactly. A few days later, it's now back in a gibbous phase. And then as it's decreasing in size, that's lit, it goes back to a half moon. That will be a third quarter moon. Okay? And what does this call it? Soon we see a half moon. Third quarter this time. This calls it a third quarter. One other place it calls it last quarter. That's not very common. Third quarter is better. Then we go back to a crescent phase, and you'll see a fat crescent, and then it gets thinner and thinner and thinner. That then is going to be a crescent moon. Anything less than half is a crescent. Okay, now, when the moon was getting bigger every night, more of it lit, that's called waxing. It's getting bigger. When after it's a full moon and getting smaller every night, whether it's gibbous or crescent, but getting smaller every night, that's a waning moon. Waxing's getting bigger, waning's getting smaller. Make sense? That's your nomenclature. Okay. Now, on page 383, is the part that we're going to do. We're going to do it today as much as we can. We may not get it all done. But we don't start at the top of the page. Why they organize it this way, I have no clue. We start in the middle of the page. The middle of the page shows the sun over there. This is exactly backwards from what it was in the book. Remember I said we're going to do something very similar to this in the lab. This is exactly backwards. In the book it had the sun over here. Now we have the sun over there. So there's the sun to our right. And notice they have blackened in half of the earth, because half of the moon is lit and half of the moon, okay? And the back half of the earth is dark, okay? And guess what? They show 8 different positions for the moon here. You can do that same thing to all 8 of those positions. The half toward the sun, the right half, I draw a vertical line. First thing I would do, draw a vertical line through every one of those 8 moons. Vertical line through every one of the 8 moons. The half that's toward the sunlight to the right, don't do a thing to it. Leave it white. The half to the back, color it in with your, I would use a pencil, but if you only have a pen, be very careful. Be sure you get the back half, the left half, color that in exactly. And from that vertical line over, every one of them's going to look just like the earth there. Just in 8 different ones of them. Really simple. Does everybody understand what I mean? I will do it on the slide. I'll back up one. I'll do it right here. Okay? Draw a vertical line. Remember that said the sun was over here, and it shows the rays coming in. So draw the vertical line, and the back half is shadowed. All 8 of those moons you do just like that. You know, everyone, I don't know why I put them like that. Okay. Draw a vertical line, the back half is shadowed. A vertical line, the back half is shadowed. Vertical line, the back half is shadowed. It's the same thing. Boy, it's not very hard, is it? Wish I could make it harder, but I haven't figured out how. Okay. You see what we're doing? Okay. That's the middle part of the page. Earth is in the middle here. Should be bigger than that, but okay. Now, notice that every one of these is numbered. This is position 1, 2, 3, 4, 5, 6, 7, and 8, right? So everybody, you have these 8 colored in. I did way too much, but this is what it looks like. Yours should look a lot neater than mine does, okay? A whole lot neater than mine, okay? Now, the next part is the bottom of the page. What you're to do is imagine you're on the earth looking at moon 1. What do you see? Say again? No. You're here looking. What do you see? Only the black side. So guess what? You're 1 at the bottom. Color in the entire moon. That's all you see is that dark side of the moon. I think there was a book written that way. I don't know. The whole moon is darkened. And you're looking up here at number 2, you mostly see the dark side, but only that little sliver that you see, you're looking here, you see mostly the dark side, you only see a little bit of this that's dark. So that it's always the side toward the sun is the whitest side, so your 2 points are going to be here, so your number 2 below will look something like, I can't do it below because I drew too light. So I'm going to do 2 down here. It's a circular moon, right? But only the part toward the sun is lighted and the rest is darkened. Right? Isn't that what you see at number 2? Okay. Number 3, what do you see?
You see light side?
Say again?
You see the light side?
You see, no, you see half of it. You see exactly that. You're looking up here, you see half lit and half dark. Do you see it?
Yes, sir.
Okay. So basically number 3 looks just like number 3 here. Now you're on the moon here. You're looking at number 4. What do you see mostly?
The light side.
The lighted side. Only a little sliver in the back is darkened. So number 4, goodness, I keep kicking this table. Okay, number 4, whoop, oops, I did it wrong. Okay, erase that. Did it like I was doing before. Okay, number 4, only that back sliver is darkened. Always the side toward the sun is light. Now, what do you see when you look at number 5? Everything is, number 5's already drawn for you, isn't it? Don't put a thing in number 5. It's, you see the full moon, right? Everything you see is light. That looks just like pi. Number 6, what do you see? You're sitting here looking here. What do you see? Mostly, it looks just like 4, doesn't it? It looks just like 4. Mostly light, a little sliver of dark in the back. Number 7, what do you see? Half moon. That's exactly what you see. It looks just like 7 there. Okay? And number 8, what do you see?
Dark.
Second? Mostly dark, but not all. You see a sliver just like you saw for 2. The sliver toward the sun is light, but the whole back side, more than half, is dark. Does that make sense? Okay. Now, we go, everybody got that? We go to the top of the page. The top of the page says, in the spaces below, write down the names of the phases according to the figures at the bottom of the page, okay? Figure 49.2 at the bottom, and include whether a phase is waxing or waning. So I'll tell you right now, 2 of these is just going to have the phase name. The new moon and the full moon is neither waxing or waning. It's just finished one and starting the other, so don't bother with that. But on the other 6, you need to say whether they're waxing or waning. So what do you consider number 1 to be? Look at your picture at number 1 there. It's a new moon. Exactly. Okay? And it's neither waxing or waning. Right before it, it was waning, and right after it's going to be waxing, but a new moon is doing neither. It's changing phase right there. Number 2 is what? You need to go back to the previous page. What was that little sliver called? A crescent. C-R-E-S-C-E-N-T. And number 2, is it waxing or waning? Waxing, because it was new with no sliver. It's sliver, the next one's going to be more of a sliver, okay? In fact, it's going to be half. So therefore, it's waxing, getting more lighted every day. So number 2 is waxing. Number 3 is what? Half moon, and that's fine. If you want to call it a first quarter moon, you can. Whichever you want, half moon or first quarter moon, either one, but you have to put a word by it. Waxing again, because it's getting bigger every night, okay? Number 4 is a word we seldom use. Second. Gibbous, a gibbous moon, and what's it doing, waxing or waning? Second. It's still waxing, it's going toward a full moon, it's getting lighter every night. And number 5 is a? Second? Full moon, exactly, and it's neither waxing nor waning. It was waxing, it will be waning, so leave that off. Number 6. Is what?
Crescent again.
That's okay.
Like crescent.
Not yet. 6 was just like 4, remember?
Uh,
It's mostly light. It's a gibbous, but it's a gibbous waning because it's getting less light every night.
right.
Okay? And then number 7.
Yeah.
It's a half moon. You could call it the third quarter if you wanted to, or you could raise your fingers if you're a football. No, that's fourth quarter. No. Okay. All right, and then is it waxing or waning? Waning, of course. Okay. And number 8. It's a crescent again. And what's it doing? Waning because it's going toward a new moon. Man, you just did most of the labs right there. Okay? Does that make sense? All right. Helpful? Okay. Didn't think we go that fast. I'll do almost the whole lab now. Okay. Number 5 we sort of talked about earlier. Okay? This is on the back side, page 384. At what time of day do you expect A, the full moon to rise? Okay? Think about where the moon is when it's a full moon. You're going to be the sun again, you're not getting too hot? Okay, all right. Huh? Oh, she's got her sunscreen on, good.
I think I got a guess.
Huh?
I think I've got a guess.
Okay, make a guess.
Midnight?
Not midnight, because the full moon is exactly opposite the sun, right? So when the sun's rising, it's setting. When the sun's setting, it's rising. When the sun's highest in the sky, it's not yet. It's exactly opposite. So when would you expect, what did it say, the full moon to rise? I just sort of said it.
Sunset.
When the sun sets, and about what time of day would that be?
5.
Yeah,
6,
let's call it 6 p.m.
6.
Or sunset would be fine. Either one you want to put, 6 p.m. or sunset. Okay? The only reason I don't like sunset is different times of year, sunset slightly different times. Full moon's always going to be rising about 6 p.m. Okay? Now, the new moon, or a very, very thin crescent moon, to rise. Again, where is the new moon? It's with the sun. And what? At sunrise, you're absolutely right. When the sun rises, so is the new moon, because they're right in line with each other, basically. Okay, so that would be about what time? Or 6 a.m. Sunrise will do, or 6 a.m., either one. The thing is, in the summertime, the sun will rise around 5 a.m., but in the wintertime, it may be closer to 7 a.m. before it rises. So, well, either way will do. Okay, we can go plus or minus an hour and 40 minutes or so. Okay, a first quarter moon to rise. Now, when it's the first quarter moon, it's over here. So it's going to, remember this is spinning like this. So the sun will rise, and then about 3 hours later, the moon will rise. So that would be around, second,
9. 8.
okay. Sun rises and about, because over here, 6 hours difference here. Is that right? No, I'm sorry. Yeah. That would be about the sun rises, okay, it's turning like this, right? Yeah, okay. So sun rises, okay, you see the sun's rising right about here. That's about 6 a.m., right? The moon is over here. It hasn't risen yet. And the sun turns to here, that's about a quarter of the way around, and that would be about few hours later, where's the sun right now? That's noon. So that would be noon, right? Noon. 3 hours after sunrise. Noon. New moon or very thin crescent to rise. I'm sorry. C, first quarter moon to rise. That would be about noon. Third quarter moon to rise. About midnight, exactly, okay? Because it's going to be about 3 hours before the sun comes up. About midnight. 6 hours before the moon. I keep saying 3. 6 hours, okay. 6 a.m., 12, yeah, 6 hours. Whew. Okay, number E, the first quarter moon to set. First quarter moon came up about noon, didn't it? So when will it set? 12 hours later. Midnight. Midnight. And the new moon, or a very thin crescent moon to set. When the sun sets, which will be about 6 a.m. 6 p.m., not a.m., p.m. Ugh. Okay, guess what? You got most of the lab done already. And we have time to spare. Okay, but that was supposed to have been 2 hours, and we did it in record time. But you still got to hang on to your lab so you can do the first 3 questions, which are from your observations. Do the best you can with it, but do not. Okay, and this will be the longest lab it's going to take you to turn in, but don't not turn it in because you got most of the answers already, right? Now those people not here, they got to figure this out. And I hope I was close enough to the computer that they heard my voice. I think I'm loud enough that they heard it, but if not. Thank you very much. No, you've been listening?
Down there, so yeah.
All right. Are your ears better than the microphone? I don't know. So you take those home, get ready for your first moon sighting. And if you can see the moon already, that's sort of bad news. Because, let's see, how many weeks do we have left in the term? The 8-week term, this is our 3rd week. You've got 5 weeks. So yeah, you'll have plenty of opportunity to see a full 2-week period up. Okay. So I would wait till the first night you see it again. Don't do it now. If you're seeing it now, wait till it comes around again. It's going to be about 2 to 3 weeks, and you'll be able to do that. Okay? All right, any questions? All right, sorry, I feel like I've cheated you out of 15 minutes of your tuition dollars, but
Absolutely not.
I'm so sorry.
I'm so hurt.
What's that?
I'm so hurt.
I can tell. Okay. All right, we will see you then on Thursday. What we'll do on Thursday then, let's make this clear. We'll start Thursday. We won't have any lab to do yet. We'll start Thursday on chapter 17. And yeah, we lost about 45 minutes today. We'll just absorb that in the lab. We'll just do chapter 17 until we either finish the chapter or run out of our time. And you will have the test on chapter 16 for the last 30 minutes. Right? Okay, so be prepared for test number, whatever it is. 3. Yeah. And also, I'll know on Thursday, hopefully, when we can go to the planetarium. Okay, tell me this while I got most of you here. Okay, we have from 12:30 to 5. Now, I'm pretty sure Mr. Weigel won't like the 5 o'clock time. But if he has a choice, if he gives us a choice, would you rather have earlier or later? Realizing that we'll be there for about an hour and it takes about a little over half an hour to get there, a little over half an hour back. So that's our lab period. We'll have class either before or after. Do you have a preference?
I'd rather do it before.
You'd rather do
But I
the...
don't care either way.
Yeah.
Okay.
I
All
think
right, so
before.
I'll let him make the deciding vote on that because it's his planetarium, so I'll let him decide. And I'll also let him do the day. If he is completely booked for the next 2 weeks, then we're going to have to do it while we're in the middle of the other thing, but we'll just take time out and go and do it. But hopefully we can do it sometime next week, either Tuesday or Thursday next week. if he's agreeable to it. I'll let him pick the time. If he likes late lunches, it'll probably be the middle of our day. If he likes the late time, then we'll do it late. If he likes 12:30, we won't be able to do 12:30 because you may be coming out of classes. So we'll plan to leave here at 12:30, get there at, I'm going to allow 45 minutes. No? Yeah, I think I'll allow 45 minutes. Do y'all know about how long it takes here to Sanford? Okay, let's say 45 minutes. So we'll say the earliest we'll meet there will be 1:15. So if any of you live close to there and want to do that first, you can meet us there at 1:15. The latest we'll be leaving there will be 4:15 because getting everything back to campus by 5. So, and y'all don't have a preference really on which part. So I'll let him decide that part. Okay, good deal.
I can need a ride, that's all.
Okay, I'll try to arrange a van.
Okay.
Okay. And you'll have to arrange a driver or something, right?
Yeah.
Oh, fantastic, super. You don't need to, I'll keep it together.
Thank you.
All right, thank you. Okay. Yeah, you think you'll be able to manage. If you can't make it, it doesn't cost you anything. You just don't get that 25 points, but that's completely optional. But if you can work it out, I think you'll enjoy it. But
Yeah, I'll figure something out.
okay. And I'm pretty sure, because I've had one class before where I had a student, and I'm pretty sure they do have access. I think it's down in the lower parking deck. You can go straight in from there.
I just gotta let him know ahead of time, so I'll just let him know we're gonna have a trip tonight,
Yeah.
and then I'll tell him I'll know.
Right. Here's a weightlifter par excellence.
Just followed.
Yeah.
I actually completed it. So
Oh, fantastic.
first time I made it about halfway through the stations and laid out on the floor in the hallway.
That's
I ate poorly for lunch. Today I ate way better. So
Okay.
because the first day I had Philly cheesesteak and all that.
that
Oh.
was probably a bad
Today I
idea.
had half a salmon.
Oh, good, man.
Yeah, I actually watched it.
I ate.
Yeah. Pretty ugly experience, wasn't it? I'm not sorry, I didn't say that. Okay. Oh, I'm recording all this. Okay, let me turn this